Welcome everybody to Linaro Tech Days. This is the rescheduled track 2 day. Starting shortly, we have Trevor presenting Empowering Edge Software Stack on ARM with High Performance Container Networking. We'll just wait until we get to 12:30. And then we'll start.
Philip can.
I can hear you, Trevor.
Yes. Can you hear me?
Yes.
Okay. Can I share my screen now?
You can share your screen, yes.
But it shows I cannot start a screen share while the other participant.
Hang on. Hang on. Okay, now.
Okay. And can you see my screen now?
Yes.
Okay, I would like to present. Yes, today's topic. Can I begin?
Let's just wait one more minute, just so we're on the half hour.
Okay.
And just to let you know, I'll give you a reminder when we're getting close to the end of your time.
Okay.
Thank you.
I think I have 20 minutes.
Yeah, 25 minutes you've got for this session.
Okay, 25 minutes. Okay.
Yeah.
Now it's time to present now.
Yep, you can start. Thank you.
Okay, thank you. Okay. Hi all. Welcome to attend this presentation about the empowering edge software stack on with high performance container networking technology. This is agenda. I would like to say that there is a 6 section about my presentation. First one is introduction. I would like to present the edge software stack architecture, and then the high performance container networking interfaces such as the Calico CDN for edge software stack. And a special SRV CNI, which named SRV, and the SmartNIC support for container networking. I would like to present some initial performance tests on this CNIs, on this container networking solutions, and our future work plan. As you know, the purpose of edge computing and micro accesses, edge computing is to bring the real-time, high bandwidth, low latency access to latency-dependent applications distributed at the edge of the network. ARM CPUs are cost-effective, consume low power, and customizable, and making them a preferred choice for edge cloud service vendors. On the other side, a high-performance, flexible, and easy deployable container networking of edge software stack is the key to the success of using ARM platform on edge cloud. Since the widely used VNFs, virtual network functions, are deployed by container-based orchestration engines such as Kubernetes or OpenShift or others. And in this graph, gives us a universal CPE example of edge compute. And the service providers are looking to simplify customer-side deployment. So we can replace the traditional dedicated appliances with the VNFs running on the universal CPE. It is a software-based system to implement all the functions implemented by the hardware appliances. So the UCPE should leverage white box servers with no proprietary extensions. And actually, the ARM ecosystem leverage price, power, acceleration advantage, and in this transition. So, in this page, I give out a edge reference stack, which is composed from bottom to the upper layer, from the bottom to the upper layer to the top. And at the bottom, we have the hardware support from the high performance NICs and or some smart NICs with high performance support. And from the network layer, we have the SLV or DPDK or something like that to support high performance network packet access. From the orchestration layer, we have Kubernetes as a orchestration engine for the containers. And but from the networking side, we leverage the older legacy networking software such as Open vSwitch or virtual vector packet processing software and the Linux networking and extended BPF to do the networking support. But from the controller side, you have a lot of choices such as the Calico, Linaro, CDN, OVM, Kubernetes, and all these solutions. I would like to present them in more detail in the later slides. From the top layer, we have the applications and application orchestration engine, such as maybe lightweight, such as ONAP, or such as the something like that. We have the application platform, such as the Kubeflow for the AI service, and the service mesh for the deployment of microservices, and the Knative, something like that. And actually, we have implemented an ARM Edge software stack and deployed it as a reference cluster with a reference cluster with a Kubernetes reference cluster. And in this cluster, we have 3 nodes. And the first one is the Kubernetes master node. We deploy the Kubernetes system service. We provided the API service in the system for the system access. And we have actually we have 2 nodes here, and therefore deploy we needed the VNFs such as the portable CNCF service mesh, such as the portable CBA service with our container with high performance container solutions such as Calico or others. And when some containers need high performance access, we can deploy the SRV interfaces by Martas or SRV CNI to the pods. In the right part is a sample deployment with small sample deployment with 2 kind of solutions. And the first one is the small deployment with malware backstop boards. It's a reference stack. And the second one is for ARM servers to deploy in the edge cloud. This is for the malware SoundX2 or Ampere servers. Now I would like to give you a total picture of the high performance container networking solutions for ARM Edge software stack. This picture give out a total of the total support in our IEC ARM Edge software stack in the Arduino community, which is open source, and give out the source code tree. In this ARM Edge software stack, we had enabled the support and deployment for several the most important container networking solutions, and they are, I think, the solutions include Calico, Cillian, and TVPP, and OVN Kubernetes, and SRV, and Linaro. I would present Calico and Cillian in later slides with little bit more details. And for the TVPP, it uses the federal VP to provide the network connectivity between ports, and it's a native DPTK support for the physical NIC. So it's a high performance with high, but it's hard to deploy and it's hard to configure and hard to debug. And for OVN Kubernetes, we have the OVS-based solution for container networking, and its performance is rather good. And we use OVN's logical switches and routers to collect ports for the outside and internal side access. For the SRV interfaces, SRV support, we deploy the physical interfaces such as the PF, the primary function or virtual function, PF or VF support for ports. It's high performance with direct Linux kernel Ethernet driver or DPTK PMD driver. I would like to present the SRV thing in more details, but usually we use SRV CNI with other container solutions because SRV is not so extensible. It's not so its scalability is not so good. So we use this Linaro or Calico to use as a default CNI. But when you need high performance access, we use the Martas to glue the 2 CNIs. And the latest one is the Linaro. Linaro is widely used and almost easiest deployment, and it's a Linux network bridge collection for port collection and overlay based communication for inter-host access. And actually, there is no good network policy support for Linaro. And in this page gives out a description about the Calico on Kubernetes. Calico as is project Calico is an important solution with widely usage, and actually this collection show the work mechanism of the typical deployment of Calico for the container networking. Actually, we have pure 3 IP networking fabric. And when there is direct layer 2 collection between the nodes, there is no need to use the encapsulation. So its performance is rather good. And we have the direct IP routing between different pods. So the access is rather direct. And the Calico solution can support the Kubernetes network policy by IP tables. And it has good scalability with the BGP-based routing for all the containers, all the pods. In this graph, I will give a rather initial performance test results for the Calico CNI on Kubernetes. And the second one I would like to say a bit more in detail is the Cilium CNI. It is widely used today and become more and more popular today because it uses and it supports a BPF-based network policy and a network to do the network filter, packet filter, and to support the container access and the pod access with BPF support. And the Cilium daemon in this graph, Cilium daemon works as a bytecode injection to translate the Kubernetes network policy into the BPF program into the kernel, and to restrict the access to the physical NIC and to the access to the corresponding pods in the system when we need to do some network policy. And from the networking model, Cilium supports the legacy encapsulation or direct routing models for the port collection, and we can use the VXLAN encapsulation to enable the access between nodes. And actually, the most typical features of Cilium is that it uses the BPF-based solution to support Kubernetes service implementation. As we know, BPF is a very high performance in-kernel solution with the network policy to do input in the kernel to do the filtering and all the things in the kernel with a virtual machine-like solutions in the kernel and to do all the things. So its performance is much better than the IP table-based Kubernetes proxy. So we should list all the services in linear list and have to use to implement all them in the linear manner. But for BPF, it's a hash-based, and we just implemented them in the very fast model to implement all the network policy. And even a senior feature for the Cilium is that it supports the API-aware security to support the HTTP or gRPC or Kafka-based API-aware network policy. For example, in this picture, we support the HTTP GET access from the different ports, and we restrict the access for the other actions such as post or such as access to other URLs for HTTP. So Cilium is a very popular and become more and more popular solution nowadays for high performance access for the container networking solutions. And another important networking solution is SRV and semantic support for container networking. In this graph, and I give a total picture of how to deploy SRV interfaces to the ports. In this graph, we use the Smarta CNI, which is glue CNI, to deploy two kinds of container networking solutions. And the first one is the default one for the Linaro Calico plugin. You can choose one of them, and you deploy the default content networking solutions to their pods. But if you need a high performance solution, such as a direct physical interface to your pods, to your containers, you can use the SRV, and you can add a description. You add a description what resources you want to use. In this graph, in this page, I give out a description of what the interfaces you want to use, and what we have provided in this page. We have provided a description for the of the physical NIC for the smart NIC Broadcom, which is Stingray Broadcom Stingray PS 200 PS 225. We use its Ethernet driver, and we use its primary functions as we give it the primary. But we wanted to use all the VFs. We should create all the VFs beforehand when you need to be used. And one interesting point maybe for you, maybe if we want to use the DPTK support, which means that we want to deploy the DPTK applications in the pod. How to use this? And so you can deploy a DPTK drivers in your description and choose the resources you want to use. This is a resource description for the DPTK based. Here, the drivers are VFIO PCI, which is a DPTK based network driver, and you can use the DPTK solutions such as test DPTK applications such as test PMD in your pods to support this DPTK interfaces. So, and this graph gives out the deployment architecture for deploying the picture about the typical pod. We have two interfaces. The first one is the Linaro Calico bridge to connect to the Linux kernel, and the second one is the SRV interfaces with a VF of the physical NIC. And I give out the networking model for the SRV interfaces collection. This is this page in the page 13. I gives out a sample deployment for 12 pods collected with a Stingray PS 225 VFs in a single host. The two two pods are collected with the SRV interfaces together by a semantic VF, two VFs, but actually it's it collected with in the same PF, but with different VFs. And the collection, this gives the collection model. And I would like to give out the some performance tests in this model, in this kind of model. And further topic here is a raw thinking on the possible model for content networking with semantic OVS offload support. It's a very raw thinking, and give out two models here. And these two models here is for the first model, we have a OVS bridge here. We provided OVS bridge with collection to the pods with VETH pair. But for the collection from this OVS bridge in the host in the user space, we use the primary interface or virtual function, PF or VF interfaces to connect to the virtual switch which is offloaded in the semantic. So, and for this topic, from the control plane, we need to provide some agent collection between the user space and the kernel space. Here we use the OVN Kubernetes solution here, but this solution is should be transferred to from the user space to the kernel from the OVN Kubernetes to the kernel to the semantic OVN Kubernetes agent. So it's a partial OVS flow offload. For the model 2, it's a OVS flow totally offload model, which is totally offloaded to the container, which has better performance than the model 1. And from the control plane, its architecture is almost the same, but with more high performance, which is because the port is collected physically to the OVS switch, which is offloaded in the smart NIC.
5 minutes.
Yes. Okay. I would like to give out an initial performance test for the Calico and for the OVM Kubernetes, which is tested in a single ARM server. And for this picture give out the performance test for the initial port to port and node to port performance. You can check it later from this slide. And actually, we had done performance tests with SRV CNI, and the SRV CNI is direct access and in a single host and across different hosts. And this is the performance test, initial performance test, which is for the SRV interface in the same host collected with PS225 VFs. And the second one is the performance test for the SRV interface in two different hosts via the PS225 VFs. And we can see that the collection is near to the line rate of the interfaces. And for future work, I would like to say that the performance evaluation and tuning for Calico CNI and Xilium CNI with port-to-port and node-to-port cases on ARM platform, mainly for cross-node. The possible tuning parameters are given here, such as MTU, such as XTX or RPS, RVFS, and some of the features. And we would like to integrate the service mesh with high-performance CNI, such as Xilium proxy with Envoy, Envoy. And we would like to investigate further incorporated container networking solutions and use the model and other things, further CIs, and more thinking on the actual work on the semantic support for container networking with OVS offload. And that's all for today's topic. And if you have any questions about the container networking, high performance container network solution for ARM edge software stack, you can ask.
There aren't any questions in the chat at the moment, so if anyone has any, please put them in. Trevor's got a few more minutes. Trevor, there's a question from Larry.
Is a product already production? It's open sourced, and we have CIs. We have CI in our Correno lab. With part of the CNIs. What is the server you used? Ampere, I think Ampere EMAC, malware, SoundX 1 and 2. What is the Broadcom single.
Okay, I'd like to thank Trevor for that presentation. And in about 5 minutes' time, we've got the next session. Thanks, Trevor.
Okay, thank you, Philip.
So up next, we have Srivatsa presenting Vertio on type 1 hypervisors.
Can I share my screen now?
Yes, you can. Thank you.
Is my screen visible?
Yes.
Okay, let me know when I can start.
Okay. And I'll give you a 5-minute reminder when we're near the end.
Okay. So can I start now?
You may start. Thank you.
Okay, hi. Hello, everyone. I'm Srivatsa. I work in the Linux kernel group at Qualcomm Bangalore. We have been working, we're playing with Vertio on a type 1 hypervisor. we saw several problems that we had to solve. So this is an attempt to summarize some of those problems and some of the solutions that we think will work. So this is the first step towards making the community aware of the problems we are seeing. And following this, we will publish some of the code we have and seek comments. So first of all, I just want to quickly say, what's driving virtualization in some of the embedded products that Qualcomm deals with. It's things like mobile phones, automotive infotainment products. One of the biggest reason is perhaps consolidation to save cost. So earlier, what we would see is, applications running in silos on separate hardware units. With modern SoCs becoming very powerful and more importantly, supporting some of the required virtualization features, it becomes easy to kind of consolidate all these applications on one hardware unit and reduce cost. While we are consolidating, we also want strong isolation between these applications, so that if one of those operating systems crashes, the mission critical ones are not affected, right? So that's one reason. The other reason is some of the security sensitive applications. By moving it to run in the context of a different operating system, we gain better isolation, so that if, for example, if the Android OS is compromised, it does not result in data leaks or in the security sensitive application being compromised as well. So that's the reason why virtualization is gaining traction in some of the products Qualcomm makes. And while doing this, we ran into how we can provide the abstraction of various devices like CPU, memory, and I/O. So each operating system or application expects its own set of resources. So how do we provide that illusion was the question we were trying to answer. So this talk is more focused on I/O device virtualization. So by I/O devices, what I mean is beyond the typical I/O devices like storage, network console. In case of embedded products, we also are considering things like your sound card, display, GPU, camera, and touchscreen. So for example, it might be possible to carve up the display so that one operating system gets a part of the display to display some whatever it wants, and the other part of the display is available to the other operating system, right? So, and the same thing for things like sound card, right? So it's possible, like, in case of automotive infotainment unit, while Android is having control of the sound card for most of the time, if the mission critical RTOS wants to just alert that some sensory information, it should be able to immediately use the sound card and output whatever it wants to, right? So how do we achieve I/O virtualization? The two approaches. One is the full virtualization, where the guest OS runs some unmodified I/O driver, and all the emulation of the device happens in the hypervisor. And this could be potentially slow compared to para-virtualization, where the guest is aware that it's running in a virtual environment, and it works cooperatively. It cooperates with the hypervisor for this I/O illusion to be achieved, right? And it's potentially way faster in terms of performance. So the framework for para-virtualization predominantly used in Linux and other operating system as well is VirtIO. So we started looking at VirtIO, what it takes to run in the environment we had, right? So this is a first brief introduction to what VirtIO is. I'm sure most of you would be aware, but I just want to summarize. So these are the key components of the VirtIO. So what I've shown in the green box is a guest operating system. It has two layers. One is the Virtio front-end driver. So this could be your storage driver, network driver, console driver. So the various drivers that knows how to drive a virtual device of a particular type. And below that is a transport layer, which knows how to communicate, how to bridge the front end and the back end drivers. So the back end driver runs in the context outside the guest operating system. It could be in the hypervisor or in another operating system. And what I have shown are these various IO buffers that need to be exchanged between the two sides, between the front end and the back end, right? And there is a ring protocol that that kind of specifies where the different IO buffers are. The key thing that I want to point out here is these IO buffers could be of varying sizes. It could be less than, it could be few bytes or multiple pages, right? And typically they are spread all over the guest memory. So you cannot we cannot enforce that these IO buffers come from a particular section of memory. It could be spread all over the guest memory. And the back end typically needs to access these IO buffers this kind of summarizes the problems that we had when implementing Virtio on a type 1 hypervisor. So what I have shown on the left is the typical environment where Virtio is used today, which is, let's say, KVM, a type 2 hypervisor. And this small box is the guest OS, and the bigger one is the some VMM like QMO or LKVM. And typically most of the backend drivers are part of this VMM, right? In some cases, it could be part of the host hypervisor itself. But the key point is the backend to a large extent has access to the entire guest OS memory. So accessing all these buffers is not a problem at all for the backend driver. So the front end has to just place pointers to these buffers in the ring and ask the backend to perform the IO, right? And the backend is seamlessly able to access all the buffers. So that is not a luxury we had in the kind of environment we were running in. So what I've shown here is a type 1 hypervisor. It could be something like Zen, for example. So the where we wanted to place the backend is in another OS. So for example, this is the secondary OS having the front end portion of, let's say, the block driver. The backend portion of the block driver will have to come from another operating system. And in general, the type 1 hypervisor that we are dealing with attempts to block access across OS memory access. So the primary the OS will not be able to access any part of the memory of the secondary OS, right? And that's required from a security and isolation perspective, right? So that was one of the big problems that we encountered. So how do we deal with that problem so that the backend is still able to access all the IO buffers that it needs to access, right? So that was problem number one. The problem number two that we had to deal with was there's something called the MMIO transport. So remember this transport. So there are various transport that are implemented in Linux. One of them is MMIO, memory mapped IO. So typically what that does is it provides a region of memory, which is a config space. And the front end driver, when it tries to access the config space, it is trapped and it is handled in the backend driver. So the hypervisor that we were dealing with, sorry, what's the question? So the hypervisor we were dealing with did not offer that support. So MMIO transport, WAT-IO MMIO transport was not easily acceptable for our environment. So that's problem number 2. The problem number 3 that we had was there was no ready to use backend that was out there that we could immediately use in this environment. So typically all these backends are part of a bigger project like KMO or LKVM or Cross VM. Taking out the backend and deploying it in this environment was not a straightforward task. So we had to make considerable modifications to make it understand that it's not running in QMO or LKVM and all that. So that's problem number 3. So these are the 3 big problems that we faced. And we kind of have a handle on the first 2. I think the third one will probably need some considerable community effort so that the backends that are part of these various projects, KMO, LKVM, and all that can perhaps be consolidated, and so that it makes it easy for for it to be used in any hypervisor environment. So these are some considerations of the hypervisor that we were dealing with. I kind of summarized some of them. The key thing is there's no support for MMIO transport. For communication between VMs, there is a provision for some message passing API and a doorbell mechanism so that you can send interrupts between the 2 VMs. The primary OS is like DOM0. It has access to most of the IO hardware and has all the IO drivers, required IO drivers. And in most cases, secondary OS do not have access to any IO hardware directly, so they'll have to go through the IO drivers in the primary OS via something like VirtIO. So this, sorry, was there? I'm not aware of the GPU this thing, but the ring structure in VirtIO that I'm shown here is very basic. It has it's more than one ring. It's the available ring and the used ring. The producer kind of adds buffers in the producer ring, and the used ring kind of indicates when those IO transactions are complete. So if that's the question, so right. So I'm kind of blowing up the memory access problem. That's one of the key problems that we had to solve. So this is the primary VM, and this is the secondary VM. The private, the white portion is what is private to each VM, right? And so there is some provision that our hypervisor provides so that a small fraction of the secondary VM can be shared with the primary VM. Now, so there is mechanism where some amount of memory can be shared between the 2 VMs. Right now, we don't want to extend that facility to share the complete address space because that beats the one of the important goals. So that if this secondary VM is running some security sensitive application, its memory should not be made available to the primary VM, right? So we want a large portion of the secondary VM memory to be private to itself. Now we are okay to have another small region of memory shared between the 2 VMs. So this is the solution we came up with to overcome the memory access problem, the first problem that we had. So what we did was we made use of the small amount of memory that's shared between the 2 VMs to bounce buffers. So what that means is when there is a IO buffer, let's say B1, that needs to be consumed on the other side, we made some changes to the VirtIO stack on the secondary VM side, on the front end side, so that it is copied, right? We bounce it to the shared region. And because the shared region is accessible to the other side, it makes it easy for the backend to consume it, right? So although it's not very good from a performance perspective, but this was kind of easy for us to get VirtIO going in the environment that we are running, right? So that we there was minimal changes needed to achieve these bounds. Mostly through DMA ops. We had to write some DMA, ops unique to this device, which will do that bounce. And we made use of the SWIO TLB driver, which has a lot of the required code to bounce buffers, right? So that was the solution we have. So we will shortly publish the changes we made to the VirtIO stack to achieve these bounds, right? So this, and the other thing we did was generally these ring, block ring, and the console ring, which kind of has pointers to the various buffers. These by default would get allocated from the private space. So we made some changes to the VirtIO front end stack to make sure that these ring buffers, these ring objects are allocated from the shared memory, right? So this kind of summarizes the changes we had to do in the VirtIO front end stack to overcome the memory access limitation problem. There are some alternate solutions that we want to explore in future, to especially from a performance perspective. So we want to explore whether we can achieve zero copy by something like a page flip, for example, right? Where so dynamically we could open up access for the backend to the buffers, to the buffers which are page sized, right? So if there is a buffer which is at least a page size, or multiples of page size, at runtime with some support from the hypervisor, if we can open up access to the backend so that it can access B1, then perhaps that avoids the bounce operation, right? So, but there are some concerns we have, and this means, at runtime we are making page table changes. So what would be the cost of those changes? Whether it would, dwarf the benefits of zero copy, right? So those are some questions we have. So we need to do some prototype and see whether it will actually, be a win that we could go with, right? And the second, the second solution we have in mind is, again, if we want to avoid the shared memory region totally, maybe we are considering whether we can use some hypervisor interface to copy data. So for example, instead of copying B1 to this region, can hypervisor copy this to a region that primary VM will decide, right? So using some hypervisor support to move data between VMs. So that's one option that we want to explore. And the third option that I think someone from Linaro pointed out to us was using a modified IO stack, something like SPDK, where we could control, where IO buffers are allocated in the first place, right? So the problem with using the generic IO stack, like a file system, is so these IO buffers are allocated way above the VirtIO front-end driver, so it could come anywhere from the guest address space. The other option that we might consider is a specialized IO stack, which moves a lot of the IO drivers into user space, something like SPDK, where we might have better control so that these IO buffers, they are allocated from specific region, right? So, and that might help us achieve zero copy. So that we have to explore. We have some concerns, however, but I'll probably skip those. So this is this is one part of the problem, how we overcome the memory access limitation problem. The second of the problem that we had to deal with was lack of support for MMIO. So the hypervisor that we are considering does not support trapping config space access and delegating the handling of that to the backend. So in the absence of that, right now wherever there was a right now we have hacked up MMIO itself, so that instead of reading and writing, instead of using readl and writl directly, we are using the message queue API that the hypervisor supports to send a message to the backend saying that I want to read, the front end wants to read or write this particular register. Can you respond? Is that okay or not? Right. So right now we have gone ahead and reused mmio.c itself, converting readl and writl to be a message queue and message queue send and receive. But the other option that we are also considering is using a totally new different transport. I believe there is some work done in this regard by the IVSHMEM project that we will also consider. So finally, the third problem that we had to deal with was there was no ready-to-use backends that would work in our case. So we had to we started with something like LKVM, which is a very simple virtual machine monitor in that works for ARM. So we heavily modified it to serve the function of just the backend. But long term, we think that it might help to come up with some from scratch new project for all the backend drivers that can potentially work across different hypervisors, right? KVM, Xen, multiple hypervisors. So if we can do that consolidation, it'll be a good thing, I think. So we have had some discussion on the What.io dev mailing list. There were some concerns expressed where that consolidation may not be straightforward, but nevertheless, we want to give it some thought going forward. So the future work is, we'll shortly be publishing the code, the changes we have done to the What.io front end to deal with the memory access limitation on type 1 hypervisors. We want to get some feedback. And we are also seeing some performance issues. Part of it is because of bounds. We want to see if we can, improve that performance degradation in any way. Right, so that's the summary of my work. I believe 2 minutes early, but if you have any queries, my email ID is listed. So I would be interested to collaborate with few of you who are trying to solve similar problems and collaborate on building a good solution for it that can be upstreamed.
Thank you for that. There are some questions in chat, if you can answer them.
MMIU is not same as IO MMU. So this MMIO is memory mapped IO. So basically, typically, this is one of the transports that What.io offers. So essentially, I probably don't have diagrams to illustrate MMIO, but this transport, we have multiple options. in What.io. So, and what is used in ARM, in KVM on ARM, for example, is the MMIO transport. So if the front end wants to read and write a particular register of the device, it's like how you would memory map the register space of a real device and read and write to it using readl and writeL. It's structured the same way, except those readl and writeLs are actually trapped by the hypervisor, and they are emulated by the backend driver. So that's the MMIO that I'm referring to. The bounce buffer, the performance good. We are seeing a lot of performance drop. And we don't know whether all of that is completely due to the bounce buffer or some other factors are in play. We are doing more analysis, so we'll, when we send some patches, we'll probably share the performance results. The type 1 hypervisor we are playing with right now is an in-house hypervisor. It's being developed, so I will probably avoid talking too much about the hypervisor that we are playing with. Going forward, and I'm expecting Qualcomm will make more details available on the hypervisor that we are working on. The sound card, yeah. So although I talked about the sound card switch, it just illustrates the breadth of the problem. It's the breadth of the devices that we are dealing with. We have not yet, played with the sound card switch. I believe there are other folks within Qualcomm who have played with sound card using the What.io stack. Some of them are probably, being discussed in the What.io dev mailing list. So we are working with partners like Open Synergy to achieve some sound card virtualization. So I don't have too many details on that. For GPU, again, I'm probably not the best guy. So there are some other groups within Qualcomm are working on GPU virtualization. I don't have too many details on that. Android in the Android we are considering in this environment, to the most part, it's like running on bare metal. There's no difference. So it'll have fast boot, it'll have USB, connections. Everything is available. So to a large extent, the Android here is running on bare metal, and it should get near bare metal speeds. Right, so the performance of Android is not influenced, or is not impacted because of having a hypervisor. It's only the secondary VM whose IO virtualization is which does not have access to those IO devices will have some performance impact that it needs to consider when accessing IO devices, virtualized IO devices.
Thank you again for your session. That was really interesting. And we'll now get ready for the next session.
Thank you.
Thank you. Next up, we have Hiroshi talking about TinyML as a service, and that will be in a couple of minutes.
Hello, can you hear me?
Yes, I can.
Yeah. Should I start to share my slide right now?
Yes, that's fine.
Yeah. Can I start?
You can, thank you.
Yep. Hello, everybody. Today, I'm going to talk about TinyML as a service. And here is today's agenda. So first, who am I? I'm a researcher in Ericsson in Finland. I used to be a Linux ARM kernel contributor, and especially working for PIOMAP and NVIDIA Kevlar. But recently, I have been doing completely different things. So, what is TinyML? The definition of TinyML is machine learning inference on ultra low power microcontroller. But this looks a bit vague, and this is only hardware perspective. So our interpretation of TinyML is like this. So you see here, there are three technological areas: Linux, machine learning, and IoT, component IoT. And historically, the overlapping area of Linux and IoT is embedded Linux. And recently, most of the machine learning is happening on cloud. It's a training phase. And machine learning inference is happening in this area, edge computing. But there is another area, IoT, machine learning, but a device which Linux cannot run. So this is the area, TinyML. And this is the hardest part because all the pain starts when Linux cannot run. So this is our definition of TinyML. So why edge computing is not enough? So this is a spectrum of the computing, and it started from cloud to compute edge and device edge and sensor. So proceeding with the sensor, resources are getting more constrained. But as you see here, 90% of the data coming from the sensors. But nowadays, those data are not processed efficiently because it has to be escalated to the above layer. And also, sensor devices can be a battery power. So battery consumption is a problem. As you see here, transmitting data consumes more energy than computer in place. So it's better not to send in a raw data, but a process in place locally. And the advantage of that is, if you look at this, this is traditional IoT. So camera is working, and the camera just sends a exact same raw image to the cloud, and it's processing in the cloud. And this requires strong connectivity, high bandwidth. But in this case, if you put the machine learning running on camera sensor, then the metadata, after process, metadata is quite small, and it can save the bandwidth. And also, it means that it saves battery, and it's a metadata, so it doesn't require, doesn't include any private data. So the privacy is preserved. There are quite good things. And also, the current boom of machine learning comes from deep neural network. But the problem is DNA model is too big to run on a variety of consonant IoT devices. So look at this. This is the TVM, one of the implementation of machine learning compiler, and it's software stack. So there are multiple machine learning frameworks. They didn't have the compatibility in the past. But now, with the introduction of ONNX, Open Neural Network Exchange format, training and inference can be executed in different frameworks. So training can be done in one framework, but inference run on any framework. But still, this has solved one problem. The another aspect is diversity of the hardware. We have quite many hardware and hundreds of AI chips are coming. And any single framework can support everything. And also, typical Python-based framework is too big to run on such constrained devices. So where the machine learning compiler is needed. So technically, machine learning compiler is the key enabler of TinyML. Then, what is TinyML as a service? So this is our answer towards the emerging TinyML technology for the connectivity supplier. So there is a huge gap between the development experience between the web and embed. Web it has a 64-bit of CPU and with gigabyte of memory and terabyte of storage, and the OS is Linux with container virtualization. On the other hand, embedded world, it has a variety of microcontrollers are used with at most half megabyte of SRAM, a few megabytes of flash memory, and variety of real-time OSs, and there is no virtualization at all. And the situation gets worse when machine learning environment. Because machine learning is started with the training in the cloud and with big GPU, and after it's trained, still it cannot fit in any machine learning framework cannot run on such embedded area. So to solve this situation, what is needed is customization. So we need to customize the machine learning models to fit into the device you use. So which means that it's like a pizza online. You need to specify what kind of topping is needed and what kind of base is needed. So this kind of customization service is needed. So this is the steps we need in the TinyML as a service. So at the first, you need to know device information. Then to find the appropriate machine learning model for that service. And that model has to be squashed into fitting into the device you run. But this is not only about the model, but you need to tune the runtime algorithm, because general purpose runtime is too big to run on the device. And build image for the operating system to run on, and it has to be orchestrated on the device. So those 6 steps are needed for TinyML as a service. Then, what does it look like? Look at this. Training, we assume training is done on the cloud, and trained model is stored in a model in the cloud. And this model cannot be run on this device directly because it's too big, and also the diversity of the hardware environment. So as a customization service, we propose TinyML as a charge. And it's backed by the multiple machine learning compilers because diversity of AI chips. So first, it collects the information from the device and download the model and compile it and appropriate image. And it's going to be orchestrated and installed. That's how TinyML as a service works. And so far, we need to support multiple backends, like multiple compilers. So we expect the backend is provided as a Docker image. It's like a function as a service. So the front end just calls the Docker API to run on, like compiling, installing, as such. And for orchestration protocol, we are currently using lightweight NPM. It doesn't have to be lightweight NPM, but this is so suitable for us right now. And this is one of the popular IoT protocols. It can export the feature of the devices in a standard manner. Also, this protocol supports SOTA and FOTA. And FOTA is a firmware over the air update. SOTA is software over the air update. So what it is, the difference is FOTA is full update and SOTA is partial update. Of course, partial update is preferable for us because it can save the bandwidth of the network. And it's eventually it saves battery. And this has supported in a standard manner. That is the good point. And TinyML service is front end is API server. So it provides the REST API to against the objects like devices, and the devices is associated with compiler, inference, and the installer. And if you host then each backend, it's trigger. And usually, IoT platform has orchestration, service orchestration mechanism. So with that, TinyML service can make use of that kind of existing infrastructure. So TinyML service can be optionally integrated into the existing IoT platform, and it can accommodate multiple machine learning compilers. So this is the TinyML as a service which we are working on. So then next is the ecosystem. So what ecosystem is needed for us? Look at this. One company, as you see here, we have the multiple backends here. So any single company cannot support everything by ourselves. And we need to collaborate. To collaborate efficiently, we need to specify standard interface for ecosystem. And currently, I'm considering those three interfaces: compiler plugin, orchestration, and inference module. And I'm looking at one by one. So first, compiler plugin. The model is downloaded and it's compiled in the TinyML service. But as I said, multiple compiler has to be supported. So which means that it's better to specify this plugin interface. But what the interface means here? So it can be categorized into two, input and output. For the input is the device information, how much RAM, how much ROM is available, and also what kind of hardware accelerator each device has. And of course, machine learning model has to be passed to the compiler. And how much quantization is needed, because quantization is sacrificing the accuracy. And in return, machine learning compiler will return the compiled module. It's a smaller version of model with specialized lambda, because developers pass runtime is too big. So that has to be combined. So this is the compiler plugin. The next one is orchestration protocol. So at first, it needs to take the device info from a device, and based on that information, we module is generated, and this module has to be passed to the device. So far, standard lightweight MTM, SOTA and FOTA and its object is enough for us. We don't do anything more than that. And as I said, SOTA is more preferred because drive update, partial drive update, and the amount of size to transfer can be saved. Also, even the device does not support lightweight MTM, we have some workaround. You can insert dummy lightweight MTM and to pretend as if device is a lightweight MTM. But on the back end, it can do this kind of flashing. So this can be used as a transitional purpose or even some product use case as well. And the last interface is module format. SOTA, lightweight MTM SOTA specifies the only protocol, and how the binary is installed, updated, it depends on implementation. But in IoT, there are many real-time OSs. But if this module format is OS agnostic, then we can save the compilation, and the same module can be used for over multiple real-time OS. That is very convenient. It's saving the effort. And I see there are 3 profiles. And the first one is general purpose, quite a rich environment, and second is embedded, and the least one is a bare metal. For the general environment, like Raspberry Pi, even Linux runs, then Onyx plus Onyx runtime is enough. And for bare metal case, you don't have any other choice than full flashing. But for the embedded case, you can use SOTA and save the transfer with this module format. And this has this kind of benefit. So those are the interface I'm looking at. And for if you use lightweight MTM, you don't do much things, but the rest of the interface has to be standardized and specified. And we cannot do it all by ourselves. That's why we are looking for ecosystem partners to specify those 3 interfaces, like AI chip vendors, machine learning compiler vendors, and IoT device manufacturers. Also, service providers are welcome. Piloting to prove TinyML as a service is useful on their business field. Okay, and I forget to mention about some talk we did. Okay, for the TinyML, we did last year proof of concept with Unikernel and OCaml, and this was presented in the Embedded Linux conference last year, and you can get all the information from this site. And there are slides. It's 72 slides. It describes quite well about what I did for in those slides. So if you are interested, please take a look at this one. And this year, I'm working on this narrowband IoT use cases with this kind of devices. And if after we get some results, I also want to publish this result too. And also, we have published those 3 articles. So what is TinyML as a service, and why TinyML as a service is needed, and how it can be implemented. So if you are interested, look at this one. And also we published the article about the TinyML as a service in IEEE, the IoT newsletter as well. So there's a link. So if you are interested, please go ahead to see that one. So summary, we are looking for partners. One is the ecosystem partner to specify those three interfaces: compiler plugins and orchestration protocols and infinite module format. And we are quite welcome. We would be very happy if you can collaborate on that area. Also for piloting partners to evaluate TinyML service in their fields. So the left side is traditional edge-based, cloud-based IoT, and like one is the TinyML as a base one. So this one, you have green sensors send raw data to the gateway, and the gateway just sends raw data to a cloud, and all the intelligence are running on cloud. This requires strong connectivity, and this is not flexible, and this requires a lot of investment. So compared with this, TinyML-based solution, raw data sent from sensors are processed on this microcontroller in place locally, and this does not require a strong connectivity, but a narrow band would be enough. And this is quite flexible and save some kind of investment at the first stage. So, for example, if you are looking for predictive maintenance, like if you want to know when the time to replace the component before it gets broken, then TinyML is one of the options, because operation downtime is so expensive. Also, if your shipped products are deployed on a wider field, which the normal network like Wi-Fi cannot be placed, then narrowband IoT can help as well. And in that case, battery power is so precious as well. So if you are interested in such collaboration, please contact me, and we are happy to collaborate with such collaboration. And thanks for listening.
Thank you, Hiroshi. There's a couple of questions in chat, if you could answer them, please.
Okay. How can I see this?
It's easiest if you stop sharing your screen. There you go.
Okay. Okay, for the question is license information in the model format. We haven't thought about that attribute, but it can be achievable over any attribute of the model. But we are more thinking about the binary module format in a lower layer. But of course, it's possible. Yes, for the question, next question is definition of constrained IoT. There's some specification in IETF, but in brutally say, I mean the non-Linux environment like ARM Cortex and CPU. So as I said, as long as the Linux runs, similar solution in the cloud can be applied, but all the pain start when the Linux cannot fit in.
Thank you again for that session. And the next one will be Paolo and Anders doing talking about recent developments in I/O control and testing.
Hi, everybody. I hope you can hear me. First
Yeah,
time I'm doing
we can
this.
hear you, Paolo. Just to let you know, Paolo, we've got about 4 minutes before you need to start.
Okay.
But we can hear you.
Okay. Did Anders make it too? I don't see him.
He's not on yet.
Oh, let me try to help me.
Okay.
To help him. Sorry.
Okay.
He says I'm there as well. Maybe I can share with him my join link. Is it a good idea to have him?
Yeah, that's fine.
Okay, let me copy.
I'm here. Can you hear me?
So, yeah.
Or is Anders already on as you? There's 2 of you.
Oh,
Anders, if that's you, can you rename your entry so I know which one's you?
yeah, maybe. Why do I do that?
It's okay, I spotted you. I'll rename you.
Sorry for that. Okay.
I think he's muted, but try to speak, but I see him muted. Okay. You are not muted any longer, Anders, now.
So you can hear me?
Yeah, I can. Now I can.
Okay.
We'll start in a couple of minutes.
Yeah. So Philip, I will share my screen and just start and then hand over to Anders, and he will be able to share his screen, right?
Yep.
Okay. I also see that nobody is using the camera, so I shut it off too.
You can use your camera if you want. It does picture-in-picture on YouTube. It's entirely your choice.
Okay. I mean, if it's, I think it's of no use. I don't know, because I don't need to show me. But if you think this is better for the presentation, I'll do it. I mean, I have no.
No, save your bandwidth. You're okay.
Okay. Yes. Yeah. That's a good point. We do have some bandwidth issues here in Italy because of so many people shifted to smart working, and of course this is an unexpected load on our internet network, let's say so.
Yeah. Okay, you can start now. Thank you.
Okay. So hi, everybody, and I hope you you are good in this tough period. I'm about to share my screen. Okay, so desktop. Okay, share. Can you see me?
Yes.
So I'll try to go full screen. So if it doesn't work, just tell me. Okay, so hoping it is working, I'm sharing my full screen. So this is a joint presentation made of two parts, two sessions. The first given by me, and it is about IO control. The other one is given by Anders, and it's about kernel testing, still related to related with IO control. My part is longer. I'll try to keep it as short as possible. I'll skip some slides. If something is not clear, just stop me or ask me after we have finished it, as you like. Of course, happy if you stop me. So as for my subsession, also my subsession is made of two parts. In the first part, I'll tell you the state of affairs, so the state of the art, and I will talk about these two new IO controllers that are now available in Linux, and I will report on what happened. It happened that I have compared them with BFQ, and I have seen that results are extremely bad, because just trying some common workloads, I've seen that these new IO controllers just fail. They fail to control bandwidth, they fail to reach a high throughput. But what is missing in the picture is the reason why these controllers fail. So the main goal of this presentation is answering this question: why do these new controllers fail? I'll answer with an analysis, somehow an in-depth analysis on these controllers. So what is the use case of interest for these controllers? The use case is when you have multiple entities that are competing for some shared storage. Examples of entities are processes, groups, containers, virtual machine, any active entity that may compete for storage. And the goal is to guarantee to each of these entities a bounded latency and or at least a minimum bandwidth. Of course, we are talking about IO here, so IO latency, IO bandwidth. In this respect, the typical mainstream solutions are extremely inefficient, because they waste almost all the speed of the drives, up to 90% of the speed of these drives. You can find all details in this article published on Linaro blog. There is a solution to this problem. The BFQ IO scheduler does face this problem and actually reduces this waste of speed to actually practically nothing, no waste. But BFQ, for a series of reasons, is not yet a common solution. So in this situation, Facebook people have, Facebook developers have contributed with two new IO controllers, the IO latency controller and the IO cost controller. The first controller associates a target latency with every group, and then it throttles group so that the target latency of each group is met. So you assign a latency to every group, the latency that you desire to satisfy for that group, and the controller tries to satisfy that latency target. The IO controller, on the other hand, associates a weight with each group, and again, it throttles group because it works with the same identical mechanism. Both controllers work by throttling IO, but in this case, it throttles group so as to let each group get a fraction of the bandwidth, of the total bandwidth, fraction proportional to the weight of the group. So the higher the weight, the higher the bandwidth. In addition, this bandwidth is inversely proportional to the cost of the I/O of that group. Cost in terms of time, how long it takes to do that I/O. So the more costly the I/O of a group is, the lower bandwidth that group gets. The idea is to avoid that groups doing very costly I/O kill the total bandwidth of a drive. With this scheme, you can also provide latency guarantees indirectly by giving the right bandwidth to a certain group. You also guarantee it a certain latency. Now, how do these new proposals compare with BFQ? Well, BFQ does exactly the same thing as the I/O cost controller because it associates a weight with each group or even each process, but this is not that relevant. But then the mechanism is different because BFQ does not throttle I/O, but it schedules I/O. So it decides the order in which I/O is to be served. And it schedules I/O so has such that each group gets a fraction of the bandwidth proportional to its weight. It's the same as with the I/O cost, the I/O cost controller. To avoid that slow I/O, also in this case kills throughput, slow I/O gets guarantees in the time domain. There is this detail, but I don't want to steal you time on low-level details about BFQ. And to finish about BFQ, as with I/O cost, you can have latency guarantees indirectly by setting bandwidth guarantees. So as I hope you have seen, the goals of these new controllers are the same as BFQ, latency and bandwidth. Yet no documentation is available on when one should use these controllers and when one should use BFQ. So this motivated me to compare these controllers with BFQ to find out when to use one, when the other, what is the performance of these controllers and compared with BFQ. I made this comparison. I have, for example, you can find my results in my presentation for Last Connect. I measured the ability to guarantee bandwidth to groups and latency to groups, and at the same time to reach a high throughput, high total throughput. What was the result? What is the results? BFQ outperformed these controllers. For example, on an SSD with BFQ, I recorded up to 47 times more bandwidth than with I/O cost, and up to 3 times more total throughput. So really outperformed them. So why? Well, it happened because for some workloads, these new controllers simply failed to control I/O. They failed to provide the expected guarantees for latency and bandwidth, and they failed to reach a high throughput. Okay, they failed. But why did they fail? So this is the goal of this presentation, telling you what I found out about the why. I will focus only on I/O cost because I/O cost is more complex and accurate than I/O latency. So my result with I/O cost apply also to I/O latency. I will show you only 3 of the workloads for which I/O cost fails on the drive that you can see on the slide. You can find a full description of the plots that I'm going to show you and full results once again in my previous presentation. So here is my first example. Let me tell you what is on this plot. So in this plot, I'm showing throughputs for workloads that are generated by 2 types of sources. The first source is a group that I call target, and this is our probe group, the one that we want to use to measure the bandwidth or the latency that can be guaranteed to a generic group for any workload. The other groups are the interferers. their goal is just to generate IO to interfere with the IO of the target. Here you can see that what the interferers do. So there are several workloads. You can see that in the first subplot, so the first workload, interferers do just random reads. Second subplot, random writes. Again, random reads, random writes. And then there are the different possible workloads for the target. Random read, sequential read, sequential read. So the various combination in this set of workloads. This is just one of the many plots that I made. So in this case, I'm comparing basically interferers that do random IO against a target that may do either random or sequential IO, just reads. Okay, so what do these plots show? They show both the throughput, the average throughput during the test of the targets, it's the bar in pink, and the cumulative average throughput of all the interferers, that is the bar in cyan. Finally, as a reference, there is the total throughput that is reached if there is no control on IO. Usually, in that case, the total throughput is higher because the drive is free to do any optimization, any possible optimization to get the maximum possible throughput. Of course, the sum of the heights of these bars gives the total throughput. Finally, what else? There are the schedulers under test, the two solutions under test. One solution is the cost, the IO cost controller, and the IO cost controller implements an IO policy that is called cost. So in the first bars in each subplot report the results for the cost policy. You can see both policy and scheduler. In case of the cost controller, the cost policy, the scheduler is known because all the IO control is in the hands of the controller. Then there is BFQ as scheduler, and the policy is the proportional share policy, which is exactly the policy implemented by BFQ. So what do we see in this plot here? We see that with cost as IO controller, the target eats all the bandwidth and the interferers don't get anything. Consider that interferers, if I remember well, are at least 7 or even 14. So all these interference altogether get almost no bandwidth. So total failure in providing reasonable bandwidth guarantees. With BFQ, you see that the bandwidth is somehow distributed between the target and the controllers and the interferers, but I don't want to go into excessive depth on this. So I hope these plots are clear. If they are not, just tell me now. Okay. The other two workloads of interest are these ones. In this case, the failure is about the total throughput. As you can see, the sum of the heights of the bars in case of IO cost is much lower than the case with BFQ. It's extremely lower. So there is a high loss of throughput, both in this case where there are sequential readers against a sequential reader as a target, and in the case where there are sequential writers as interferers and the sequential reader as target. So this is the second type of failure. So first type, failure in guaranteeing bandwidth to the interferers in this case, but there are other examples where the failure is for the target, and in this case, failure to reach a high throughput. Okay, so this is the problem. So I started analyzing it. To do that, I made a patch to trace what happens inside IO cost. And this is what I found. The root cause for all this failure is this one. Drives have a very complex transfer function because they have multiple channels. They have pipelines inside the channels, they do striping, there is parallelism that depends on locality, there is interference among workloads inside the drive, there is read ahead, request reordering, garbage collection, wearing, and a lot of complex stuff. So for this reason, the parameters of the transfer function of these drives are non-linear. They vary with time, they vary with workloads, and they are hard to know or to decide. So the transfer function is a function that tells us the output, so what happens, which IO requests are served and when, as a function of the input, the IO requests that we dispatch to the drive. So complex transfer functions, and the problem is that IO cost and IO latency control IO exactly through these parameters. In particular, IO costs are the parameters used by the IO cost controller. So the IO cost controller uses the IO costs, the cost of each IO as a parameter to control IO, and uses device saturation. So how loaded the device is. And these are exactly the parameters that are not linear, that vary with time, that are hard to know precisely. So depending on the actual transfer function, it may be hard for the controller to actually control the bandwidth of the groups and to boost the throughput. So I know that these details are maybe somehow not so apparent. The problem beneath all these details may be not so apparent. So I will go for a real life example that maybe will help us grasp the essence of the problem. Then I will apply this real life example to the failure of IO cost. So here is my real life example. Building where it has been put little or absolutely no care in having a stable and easy to control system for heating water. An example is, unfortunately, my house. So suppose that you want to take a shower in such a building. Getting the shower temperature right may be a problem in this building, because when you rotate the knob of the shower, you stimulate in a nonlinear way a nonlinear system. It is a system that reacts with time varying delays. So here is what happens. If you don't know these parameters well enough, you may fail to control the temperature successfully, because you may get too hot water or too cold water until maybe you learn how to rotate the knob. But even after you learned that, so you made it, so you have control on your temperature, there may still be external events may change these parameters, so you get burned again, even if you didn't touch anything. So I hope that this example gives you good insights on the actual problem. So for IO costs, controlling IO, so guaranteeing fairness and reaching a high throughput is as difficult as getting the shower temperature right in my example building. That's the idea. Now I will focus and I will show you some details only for one failure, the throughput failure. If you want, I have extra slides about the other failure. Let me tell you very, very succinctly the parameters used by the IO cost, because I will show parameters. So IO cost has the throughput through a parameter named vrate, which is computed as a function of the busy level of the drive, that is how busy the drive is, and as a function of how many groups are lagging behind their target service, and finally as a function of the device saturation computed through latency of IO, but I don't want to go, again, not to give you too many details. But this busy level and number of groups lagging are a function of the estimated service received by each group. So they are a function of the IO costs. But IO costs are subject to high imprecision for all the reasons that I've already told you, and they are time variable. So this is what happens. This is a trace of what happens in the failure where there are only reads. So the throughput failure with only reads that I showed you. You can see the red line is the V rate, so how the controller sets the speed of the drive. And as you can see, at the beginning, everything is okay, but then there is this drop here, and the drop happens because, as you can see, there is this peak in the busy level. For some reason, the controller believes that the drive has become suddenly extremely busy, which is completely false. So it drops the V rate, so it just slows down the drive for no reason, and then it keeps it very low. Then there is some other fluctuation where it seems to realize that actually the busy level is lower, but then when it tries to increase V rate, again a peak, so the V rate goes down. Then again here a very high peak, even lower V rate. Then it tries to increase again the V rates, but there is a high number that you can see with the green here, a high number of groups lagging behind the target service. And in this case, it's harder because of the algorithm to increase the rate quickly. So the ultimate result is that on average, the throughput is extremely low for no reason. The drive is completely underutilized. So that's the reason for the failure. Similar failure with the writes, but I don't want to steal time to Anders. So believe me, this is the same problem with different cures. So to wrap up, IO cost and IO latency for sure have been crafted very skillfully and have been tuned to get the shorter temperature right on the machines of the others of these controllers. But if the transfer function varies, then these it may be hard or even impossible for this controller to win, to control IO. Why does BFQ make it? I will leave this on extra slides. I don't want to comment on this. If you want, I will tell you now. I don't want to steal time to Anders. So for me, this is all. This is all for my part, and I hand it to Anders. So let me switch back to not full screen and stop sharing.
That's okay, Paolo. Anders can just start sharing straight away. And take over.
Okay. Thank you, Phil.
About
Okay.
how we try to test Paolo's stuff, and I'm working for a project called LKFT, and today we only do functional testing, and Paolo's been my guinea pig for benchmark tests. And as Paolo pointed out, he found some issues, and to present and to find all the regressions, we've done endless loops how to do this. First, we think we need, or I'm going to make this really short instead. Can we run on any platform and do the test, or do we need to have one hardware and one peripheral and run that over and over again? Or can we have a pool of devices and peripherals to run? That depends on benchmarks, what we want to benchmark. And for Paolo's S-Suite, we think we can use a pool of targets, because it's only a regression if it's more than 10%. That's what we're gonna start with at least. And we're using we will use a tool called Squad Client to do email reporting at the end as well. But I think I'm gonna stop here. We're out of time.
Thank you, Anders and Paolo, for your session. And next up, we have Antonio talking about improved Android testing in love with Docker, and that will be at past.
Hello. Do you hear me okay?
Hi, Antonio, yeah.
Okay, for a moment I thought I was caught in the daylight saving change and lost my my time by 1 hour.
No, you're fine.
Do you hear? Let me share my screen, see if it works. This will stop other screen sharing. Do you want to continue?
Yeah, that's fine. You can start
okay.
with the show.
Do you hear my presentation window? Do you see it?
Yeah,
And now full screen. Is it too good?
that's fine.
Yeah, okay.
Okay, Antonio, thank you.
Should we start?
Yes, please.
Yes. Okay. Hello, everyone. Good morning. Well, it's good morning to me. I don't know about you. I'm going to present about this project that I'm working on for the last half year, together with the Lava team. When I started contributing back to the team, I thought it was going to improve Android testing, but now I realize it not only improves Android, but also all the areas of Linaro work that are going to be tested on Lava are going to be impacted by this. And that's why I'm planning to present today. A little bit about myself. I'm a software engineer at Linaro. I used to work on Squad. Now I'm working on the Lava team. I'm a long-time free software developer. I'm a member of Debian. And I also am drive-by patch contributor to lots of projects. So lots of one-time contributors to several projects. And then our agenda today, I'm going to give a very brief introduction to Lava so that we understand the context in which this work is being done. I'm presenting the use cases for using Docker in Lava. I'm giving an overview of the current solution where we are using LXC and the problems with it. I'm giving an overview of the new solution based on Docker and present the current status of its deployment in Lava itself as an upstream project and in the Linaro labs. So a brief introduction to Lava. Lava stands for Linaro Automated Validation Architecture. It's basically a test execution system. So it has the goal of running testing software on real hardware. So it includes deploying operating systems to the boards, booting them, and then running tests. It has several usages. It's used by kernel CI, for instance, for doing boot testing. LKFT is a Linaro project that does system level testing. So we test mainline kernels and LTS kernels against several use cases and report that back to the kernel community and to Linaro customers who use that project. It can also do power consumption tests, benchmarks. It also supports running multi-node tests, which are tests against multiple devices, so you can test communication between them and other types of inter-device testing. So Lava tries to automate testing, the type of testing people usually do manually with development boards on their desks. So when you're doing this type of development, you have to, the developer has to control power somehow. So maybe people are unplugging and plugging boards, but maybe they have power relays that are controlled remotely. Then that's how they turn on and off the boards. They have to have a way of getting to the serial console on the board. So usually people use serial relays or even direct serial connections. Then you have to control the board to download the kernel and a root file system from somewhere. And then you run the board, then you get a shell on it, and then you run your tests, and then you power off the board and start things all over again. And the point of Lava is automating this. So you submit a test job configuration, which includes, among other things, the software you want to run on the board. So it can be a kernel, a DTB, a rootfs. And there's a machine that controls each board, which in Lava terms, we call it a dispatcher, which will control power, serial connections, will control how the software is provided to the board. It can be via NFS or TFTP or any other method. And that's going to automate the manual work we usually do with development boards. So in Lava, we have a server, which is the component that receives the job definitions. And we have one or more dispatchers, which are the machines that are actually connected to the board, that you have the power control, the serial relay, you serve files to the board, and so on. And the use case we want to solve here is running arbitrary code on the lab infrastructure. So by definition, you can already run arbitrary code on the test boards, because Lava has the mechanism to recover if your arbitrary code does something wrong. So if your test switch crashes the board, Lava is able to recover it. If you flash a bad kernel, Lava is able to recover it. But then if you do that on the lab machines, first the lab people will not be happy at you, and then we'll have to manual work to recover the lab. So that's not good. So for some types of testing, we want to allow users to run arbitrary code, but we also don't want them to run arbitrary code on our infrastructure. So there's going to be a middle ground there. So today, some of the use cases that use this functionality is, for instance, Android testing. So a lot of the Android testing with CTS and VTS involves running tests from a host machine that runs ADB, fastboot, etc., and connect to the device under test. And that's one of the use cases we want to support. We want to support people running their own ADB and fastboot binaries. Maybe they are testing the latest Android development kit, or maybe they need some feature that's not available yet in the binaries we have in the lab. So that's another use case. Another use case is manipulating downloaded images. For instance, you usually need to include kernel modules into the rootfs you are building. So you don't want to rebuild a new rootfs with every kernel. Instead, you want to just get the kernel modules for that kernel, inject that in the rootfs. So that's something you can also do if you are able to run arbitrary code in the Lava infrastructure. And also another use case we are starting to support now is running custom QEMU binaries. So usually you have the QEMU binaries that are available in the lab system, but then also you are developing QEMU itself or KVM for the kernel, and you want to test that against the usual Lava infrastructure. So then you need to be able to run arbitrary binaries in the infrastructure. So right now we support that using LXC. You treat LXC basically like a regular Lava device. You deploy some file system to it, you boot it, and then you run tests. You run the code there that you both install any dependencies you need and do the job you want. And as I said, the test job needs to contain explicit instructions to install the needed software. So you want to pull ADB and fastboot from somewhere. You want to connect to the board and do your thing. This makes the job definition a little long and complex, more than is necessary. And for instance, today to run the Android test suites against a device, you need to first deploy a LXC container. So you have to declare, I want a LXC container that has this base system. Then you have to tell Lava to boot that container as if it was a regular device. Then you need to have a test definition that install the necessary tools inside the LXC container. Then you get to the real work, which is deploy the image to the device, boot it, and then run tests from the LXC container connecting to the device. And then here we have a brief comparison of LXC versus Docker. None of what I'm saying here is to badmouth LXC. I happen to be one of the maintainers of LXC in Debian, so I think it's a very nice system. It's just not suited to what we are trying to do here. So LXC stands for Linux containers. It's a system to manage full system containers. That is, those containers, they boot, they have an init system. So you have PID1 inside the container. Your regular services start as normal. So if you have a web server inside the container, it will start normally. And the whole point of LXC is to make the containers look and feel like VMs. So it's you have less overhead since you don't have to emulate a system. So you have all your processes there, and you don't have the overhead of running a second kernel. On the other hand, you have the security problems of not running a separate kernel. So there's a trade-off there. And one of the points of LXC also is that usually you only have available vanilla OS images. That is, you have a clean Debian install, you have a clean Fedora install, you have a clean Ubuntu install, and then you have to install your things on top of that to be able to use the container. Docker, on the other hand, is suited to application containers. So it executes only one application, usually with a very small fake init system. So usually you have a minimal PID1 in the container just to manage, to control the actual application that's running there. You don't have system services. So if you have a Docker container that has a web server inside, it won't start automatically. You have to manually install, start the web server. And you have images that are distributed with applications pre-installed. So you do have the vanilla OS images that you can base on to create your application containers, but you can distribute the containers with everything that you need already installed. And that's makes it easier to deploy applications because you don't have to do anything. You just grab the container that already has the application installed and then you just run it. And as a curiosity, in the early days, Docker actually used LXC as the container runtime under the hood. These days, it doesn't anymore, but in the early days, there was a nice nice relationship of mutualism between the platforms. So now in Lava we have Docker support. So this brings us a little few advantages. One is you can use any available pre-built image with the dependencies already installed, so you don't have again to start a container and then install things in it. You just grab the image that already has the things you need installed, and it also lets us have a lot shorter test definitions in Lava. So the test definition to do the same thing using Docker is a lot shorter than the one that does the same thing on LXC. So we will have examples ahead. So we support those use cases that I mentioned in the beginning. So you can run ADB and fastboot inside Docker for deploy, boot, and test, because you want to run custom ADB and fastboot binaries, because you want to run the very latest Android development kit, or for any other reason. And that's available since Lava 2020.02, which was the latest release of Lava. You can manipulate images after download, so which is what LKFT does today. We have examples of all of them later. So that's merged into the master branch, and it will be available in the next release, which we are working on it these days. So it'll be available very soon. And also the custom QEMU binaries, the support for it is also merged and will also be available in the next release later this week, I think. So now I have a few examples. I didn't even bother to show the old way of doing this with LXC because we consider that deprecated and we want to move on to use Docker because it's simpler and faster. So first example is running ADB and fastboot on Docker. So you have a regular deploy definition, deploy action in your job definition. The only difference is that now you specify a Docker image. That's all. You specify the images as you did before with URLs to the images and their names, and then you just get ADB and fastboot inside Docker. So you have to provide your image. In this case, the example uses an image that's called ADB-fastboot, and it just works. It will run fastboot inside Docker container, and Lava will share the device node with the container under the hood, and it just works. Fastboot gets called from inside the Docker container, and it does the deployment of the images. Then to boot the device, again, same thing, you just specify a Docker image, and then the fastboot boot method for Lava will just run fastboot inside Docker, and it will just work. And for testing, also you just add the Docker image declaration, and then you have your usual test definition for Lava. The only difference here is that this test definition will run inside the Docker container and not inside the device on the test. So for people testing Android, it's like before. So the test definition was run in the LXC container. Now it runs in the Docker container, which with the difference that it's faster and it's simpler because you can have your container with everything you need already installed. You can even have the test suites themselves inside the container again already. And then you just specify a test definition that will run inside that container and will start the test for you. A second example is manipulating downloaded images. LKFT uses this today with LXC, and the job definitions are more complicated than necessary. And now we are able to migrate to this new way of doing things. We have now a new deployment method called downloads. So you specify the image you want to download. So in this case, we have a kernel, we have a modules tarball, which was built together with the kernel, and we have a rootfs. In this case, the rootfs is some fixed rootfs you want to use for all the jobs, and the modules are the ones that were built together with the kernel you are using for this test. And then you have now a post-process section for the deployment, where you specify the Docker image you want to use and what commands you want to run in the Docker image. In this case, we are in this example, we are using Kir, which is a tool developed by the LKFT team, which does this merging of images. So it will, for instance, take the rootfs image and inject the kernel modules inside it and generate a new image with the rootfs already pre-populated with the kernel modules. And then it modifies the files in place where they were downloaded. And then you do a second deploy to the device this time with two differences. You specify you want to do the deployment from a Docker image, and you want to get the images from the downloads protocol, which is a fake protocol we have in Lava now to access those files that were downloaded in the previous step. So you downloads, you do any processing you need with the images, and then you can refer to them later in the test job by using the downloads pseudo URL scheme. Then you can get your, in this case, you see here boot.image and rootfs.image were files that were created by the post-processing in the previous step. And the third example is running a custom QEMU binary. It's very simple as well. You just use the regular QEMU boot method and you specify a Docker image. So if the Docker image runs the QEMU binary by default as the entry point, then you don't have to specify a binary. Or if the image just has the binary and you need to call it by hand, then you pass the path to the binary, and then Lava will start the VM with that QEMU binary inside the Docker image instead of whatever QEMU binary there is in the Lava machine. So a few closing remarks. As a reminder, we have the ADB fastboot support for Docker in the first example already available in the latest Lava release. The other two will be available in the next release. And future work that they're doing in the short term, we are going to do a LXC to Docker migration guide to help people migrate their jobs over to the new Docker support. And we are also now working on improvements to Lava itself to be able to run the entire Lava dispatcher as a Docker container that will unlock a few other use cases we have. For instance, to making it easier to deploy Lava. And that's all I had. I will open the chat window now to see if we have questions, but feel free to ask. Okay. Paul asks if all the stuff is described in the Lava docs already. So no, we are currently reformulating the Lava documentation, and we need to do an effort to document things, but they are documented in the release notes. So every time you do a release, we write some documentation for in the release notes. So if you want to use those features, you can check the release notes. They are there, and we are working on having updated docs. Larry asks, in the first test action, we install something in the container. How the second test action could share the packages which was installed in the first action? Looks like no persistent Docker container supported here. Yes. So the point is, you provide your container with everything already inside. So you don't have to install anything inside the container. So when we say here use this image, then we assume that everything you need is already inside the image. So you shouldn't need to install anything in the container at the job definition stage, at the Lava test job. So you provide your container with everything you need already inside. And that makes it easier because you can test your container locally after building it. And after you push that to some Docker Hub, you know that exactly what you pushed is what going to run on Lava. So you don't need to test the installation process. You do the installation process as a regular Docker container build, and then it's available. We have 1 minute to go. Any more questions?
There's another one from Stephen.
From?
Stephen Lawrence is not showing up. Sometimes host fast boot flashing is simplified into a script. Is it possible to use such a script in the new scheme, perhaps via download manipulation, thinking of deploy stage?
Yes, the step you provide for the deployment are arbitrary shell commands. So wherever you do that, you run inside the container. You already have access to the device at that point. So if you want to do the deployment yourself, calling ADB by hand from the post-processing, it's possible. We didn't think of it yet, and I never tested, but it should work.
And one last question. Drew asks, can this be used for U-boot?
For U-boot. Yes. So yeah, another use case that I didn't mention is if you want to run tests against a U-boot shell over serial, for instance, you want to give no inputs to U-boot and then test that U-boot does the right thing. Yes. So yeah, I forgot to add this detail, but you have the serial connection between the Lava dispatcher and the device is also shared with the container. So you can, from the container, connect via serial to U-boot and then run whatever test you want. Yes.
Thank you, Antonio.
Thank you.
Next up will be Zen-based automotive reference stack using Yocto. That will be in a couple of minutes. Thank you, Bertrand.
Hi, can you see my screen?
Yes, I can. Thank you.
Okay, so good morning, everyone. So today we will present you the Xen-based ARM autonomy stack using Yocto. My name is Bertrand Marquis, and I am a principal software engineer at ARM in the open source software group. I am working on the Yocto autonomy reference stack that I will present today, but I am also working on Xen on ARM. I will be presenting today with John Mason. John, I will let you introduce yourself.
Sure. So I'm John Mason. I also work at ARM, I guess indirectly with Bertrand. I'm kind of the principal Yocto developer at ARM. There are many other Yocto developers inside ARM, but I kind of help corral them and focus them upstream. I'm the principal maintainer of Meta ARM Open Embedded Layer, and I'm also an Open Embedded board member.
So today we will start the presentation by explaining you why ARM is creating the autonomy reference stack and what it is exactly. We'll then detail the work of ARM on Yocto with the Meta ARM layer and how this is used for the reference stack. And finally, we will give you a status update on the current implementation and what can be expected in the future. So first, why is ARM creating a Xen autonomy reference stack? So autonomy systems are very complex. That's systems like self-driving cars, but also robots. A self-driving car includes complex input processing, like video or LiDAR, number of computation going from artificial intelligence to voice recognition, and several output handling. That's managing the engine, but that can also be playing music on Android Auto. An hypervisor can make development easier by splitting the system in different components. Each one can be implemented by different groups or companies. It can be used as a generic platform to have functions developed independently of the hardware and reused on different systems. It can also make development easier by isolating critical from non-critical parts, reducing certification costs, giving more control on the boot flow, or allowing independent update management of different functions. So why choosing Xen? So first, Xen is a type 1 hypervisor, means it does not need a rich OS as host. This is reducing the amount of critical code and enable faster boot time to critical functions in comparison to what you could do with a type 2 hypervisor. Xen is open source and has a wide community of users and developers. It is used in a number of servers and applications, and Xen community is pushing towards embedded systems. FUSA project is looking at the Xen certification, while several industry leaders like ARM want to help Xen being more suitable for embedded systems. For example, there is a Xen automotive group that you can find on Xen website. With the autonomy reference stack, we want to create a Xen-based stack suitable for autonomy systems. The stack will focus on boot time and strip functionality to be suitable for embedded systems. The stack will provide a small and simple way to manage guests, from how to start and stop Xen to a deployment system suitable for embedded application. The stack will include features focusing on safety and security, like opt-in integration, secure boot, or update problematic. And finally, the stack will provide an easy way to integrate different components and have guests usable on different systems. This slide shows the blocks of a system based on the autonomy reference stack. All components in light blue are the focus or will be the focus of the stack. So first, you have a firmware based on trusted firmware from ARM and Opti. You have the Xen hypervisor, a DOM0 Linux with tools to manage guests, and then guests based on Linux, but those could be also based on other RTOS, and those guests will contain the actual workloads of the system. So I will let John handle the Yocto part.
In the previous slide, you saw talking about a reference stack, but how do we build a custom reference stack? And the easiest way is with Yocto. So the Yocto project is a set of templates, tools, and methods that help you build custom-based Linux systems. So if you're looking over to the right, you might see kind of a bit of an eye chart of different pieces interlocking together, and it might be quite confusing. But the pieces that I want you to kind of focus on here are in the lower right-hand corner. You'll see images, and essentially this is the process of how images are created. And over to the left of the infographic is a, I guess this is an infographic, but a graphic, is the layer piece. So what you'll see are how these pieces all pull together, and also kind of notice up in the upper portion of it, the source code and the source mirrors and how it's being fetched down. So this is, I don't want to dig too deep into the details of Yocto and how it's happening. So hopefully everyone has at least a rough understanding of Yocto. And yeah. So the meta ARM layer. So essentially, we've created the layering aspect that from the previous page, and this is kind of how it's made up. So you have your own custom Linux distribution to your to the right and the left, and each of these is done by layers. And the layers are made up of individual pieces. It's meant to be highly modular. So each of these layers is made up of recipes. And if you look down at the pieces, you'll notice that some of these are duplicated from the right and the left. And what that's meant to show is kind of common dependencies. So the dark blue on the left, you'll see meta ARM BSP, and in the right, you'll see the red and meta ARM Xilinx, for example. And what this is meant to show is that you can easily remove a piece and replace it with another that has the same dependencies, and that's the kind of modularity that Yocto has. And also you have the side-by-side pieces that make up your custom distribution. So for example, in it, you're going to need a kernel, and the kernel will be made up of, will come from the meta ARM BSP, and that'll be applying patches on top of meta ARM. So that's what this graphic is meant to show. So why do we go through this effort of making a custom layer, which we are calling meta ARM? Well, unfortunately, there are many ARM, well, fortunately, there are many ARM vendors. Unfortunately, they're kind of doing their own thing. So we have each one doing their own unique Yocto layer, making divergent recipes for things like kernel and U-boot. And each one is a different version of Yocto. And because everyone's doing their own thing, there's no intrinsic need to upstream. They're just pushing random, or not everyone, but some are pushing random Git trees to GitHub, for example, with just their changes on top of a snapshotted tree. And this creates a large problem because it makes it difficult to upgrade to new versions of Yocto and the underlying software. And by this, I mean, in later this month, a new version of Yocto will be coming out, Dunfell, I believe it's named. And if you were 3 versions behind, snapshotted to all this stuff, it's almost impossible to force an upgrade, or it's not impossible, it's extremely difficult, a lot of hours to put in that's unnecessary. So, and because of that, there's no shared work because everyone's doing their own thing. And because everyone's doing their own thing, you don't know how well each layer and each recipe is tested. And the kind of final nail in the coffin is that they're often not following the ARM recommended processes or implementations. For example, ARM would really, really love for everyone, all the ARM BSPs to be running Secure Boot and Opti, so we can have the highest level of trust and security. And because there's no shared work, a lot of these vendors will just get it working and throw it over the fence. So Meta ARM is intended to be the one-stop shop for all of ARM software. Kind of to answer all those problems on the previous slide, where we're making it, we're pulling in all the ARM specific software, all the reference hardware and the BSP enablements, the tool chains, the autonomy, and maybe even some distro reference distros. Also, this is intended on being a place to collaborate so that ARM vendors can, from 2 slides ago, can take the pieces they care about for Meta ARM and use that in their own reference layers or meta layers. So for example, Meta Xilinx can take the trusted firmware recipe and just apply their stuff on top and not need to maintain the core of it, just their own unique piece of it. And because of it all being a single place, we can run CI, continuous integration on it constantly, so we have stability and quality in it. And I think most importantly for me, we want ARM to model the behavior for all ARM platforms, and hopefully all vendors see it and see it as a good thing and just copy the relevant pieces so they don't need to do the work. And that's that'll save a lot of effort on everyone's plate there. So Meta ARM is made up of a bunch of different pieces, and most confusingly, we have Meta ARM. So the confusing part here is that Meta ARM is a collection of layers, and inside that we have the core pieces of layers, which we are calling Meta ARM. So these are kind of the generic recipes. For example, the trusted firmware A recipes, the Opti recipes, and recently we pulled in something called OpenSCD support. So this is really just kind of the core pieces that other layers will want to reference. And Meta ARM BSP. So I'm sure many people out there have heard of the Juno board. This layer will provide basic support. There's already support out there in the Meta Linaro layers, but because this is ARM reference hardware, we should be the best ones to support it. And so we've had many communications with the people working on Yocto inside Linaro, and we're transitioning to Meta ARM. In addition to that, we have the software foundation models, also known as FEP, which enables you in software to model the ARM references or ARM designs, and enables you to test it 100% in software. And we also have some hardware platforms, and more will be added to that in the future. And then we also have Meta ARM toolchain. So Linaro people will probably remember the ARM or the Linaro binary toolchains and software toolchains that they've been developing for years and years and years. In the past year or two, that has been transitioned to that's been transitioned to be supported by ARM. And ARM is every year, I believe twice a year, releasing software releases of GCC and binary versions of the same GCC tool chains. They are currently 8.2, 8.3, and 9.2. And in this layer, you can easily add these to be used inside your Yocto layers.
So the Meta ARM autonomy is another sublayer present in Meta ARM. and is an implementation of the reference stack I presented earlier based on Yocto. So it can be used to build all components of the stack from the firmware, Xen, and DOM0 to guest. This layer can be used with other layers to use external BSPs, recipes, or workloads like AGL or waylanding guests. It is designed to be easy to use and suitable for fast prototyping and research. The first part of the autonomy stack is building the host system with the firmware, Xen, and the DOM0 Linux. So Xen is built based on the meta virtualization recipe, which are already existing. The layer is also providing a way to build a Xen compatible device tree created from an existing DTB, but adding the parts required to boot Xen and DOM0 Linux on top of Xen. A DOM0 Linux is built with Xen backend drivers and required tools in the root file system to manage the guests. So this is implemented as a Yocto distribution feature named ARM Autonomy Host. The layer also provides an image named ARM Autonomy Host Image Minimal to create a minimal DOM0 system with all required tools to manage Xen guests. The second part of the autonomy stack is building guests. The layer provides a Yocto distribution named ARM Autonomy Guest for that. The feature will add Xen front-end drivers in Linux kernel and some customization to be able to run as guests, that, for example, having the console on HVC Xeon. There is no specific image provided for guests, as the feature can be used with any existing Yocto image. So it can be tried with the Yocto core image minimal, for example. The layer also provides a BSP named ARM64 Autonomy Guest. This BSP provides a minimal kernel configuration suitable to run as a Xen guest. It can be used to generate platform-independent guests, only relying on Xen front-end drivers for communication. The meta-ARM autonomy layer is introducing the Xen guest system. This is a minimal Xen guest image and management system. A Xen guest image will include all components required to build a Xen guest. So that's the kernel, the device tree, but also the configuration, a definition of the disk and its content, and some initialization scripts that will be run on the host when starting the guest. The Xen guest MK image tool is used to manipulate such images. So that's creating or modifying them, but also extracting them. And the tool can be used on both your host development system and on the target. The Xen Guest Manager is a tool to be used in the DOM0 system to manage Xen guest based on the Xen guest images. So the manager will start and stop your guest, and it can also use LVM to create disks for the guest based on the configuration they include. It also provides an init support so that your guests are starting automatically on boot. So the Xen guest system is integrated in Yocto with several components. The first one is a file system type, which is used to create a full Xen guest image when you build a Yocto image. So that includes the root file system and the kernel, but also the Xen configuration. We provide a class named Xen Guest Image Extra that can be used in recipes to extend this image. That's, for example, providing an init script so that you can customize your guest when you start it. The Xen Guest Manager is included on the host image to manage guests created with this. We also provide a network bridge system, which will create a bridge on the DOM0 to which guests can connect so that they have connectivity to the external world using network. So the layer will include lots of parameters so that each of those components can actually be customized, from what amount of RAM you want to the guest to what this partition should be used to create LVM volumes. So let's conclude today's presentation by giving you a status and what you can expect from meta-ARM in the future. So first, meta-ARM was deployed in January 2020 in the Git Yocto project, and the first feedback we had is very promising. First beta of meta-ARM autonomy has been pushed to meta-ARM mailing list last week and should be merged shortly. We will release our first stable version with Yocto Dunfell in April. in the future, we will add more BSPs to MetaArm BSPs. So that's, for example, one for Corestone 700 or for the N1 SDP board. We will add more software support to MetaArm. So there are plans for an EDK2 recipe or an SCP recipe. And we will continue to enhance MetaArm autonomy, optimizing the boot time, the size, managing security, including OPTI, make development easier for everyone, and add compatibility with other layers, for example, with AGI. So for more information, please go to the Yocto project documentation. You can clone and use our layer, and you can join our mailing list if you need help or if you want to contribute to MetaArm. Thanks, everyone. So if you have questions, I think we can answer them now. Okay. So, Paul, in all this stuff described, well, that's, I guess, for the previous presentation.
Yes, I'm not sure we've had any questions. Oh, there we go.
Okay. What is the difference between DOM-U and DOM-0? That's a question from Drew. Well, DOM-0 is the part in Xen creating guests. A DOM-U is a guest which has in Xen naming scheme, that's just a guest which has no access to any hardware devices. So it's only relying on Xen drivers to have access to stuff like disks or Ethernet. So it's only using virtual drivers. So Peng's questions. How to secure boot for a DOM-U. So the idea is to handle this part from the DOM-0. So DOM-0 will be secure boot. And in the chain of trust, DOM-0 will actually check the image, including the kernel, the file system, and all components before starting a guest. So you build a chain of trust. DOM-0 is trusted, then as DOM-0 is trusted, it can check the guests before starting them. So then we have wrong window. Okay, anyone else has question? File system checking can be time consuming. Yes, it can. That's why we have to do some research on this. So the initial file system can be checked, but then if you have checked the initial file system and you let your guest run and you check only the parts that you update, you might be able to handle some updates in a fast way. But definitely, yes, I agree that can be time consuming, but it will be application dependent. Maybe you will not need to check it. What platforms qualify for being in MetaArm instead of Meta vendor like MetaFSL or MetaTI? I guess this is more a question for John. John, do you want to answer this one?
So sure. So this isn't intended on taking from Meta vendor, for example. This is intended to supplement it. So for example, you talked about Meta TI. So what we'd like is for Meta TI to be dependent in the parlance of Yocto and Open Embedded. We like it to be dependent. So we would pull the recipe for trusted firmware from MetaArm, and then inside its BSP portion, it would augment that recipe through a BB append and, for example, overwrite where the source is coming from, and then use that BB append to build their specific TFA recipes.
So on this question, MetaArm BSP itself is supposed to be the place to hold BSPs for ARM produced systems. So that's more emulators like FVP, Juno boards as a development board that you can get from ARM directly. It's not supposed to hold any BSP from vendors like Xilinx or NXP or Renesas, for example. Those vendors will use MetaArm to retrieve the trusted firmware recipe, but will not use MetaArm to put their own BSPs. That's not the aim of the layer.
Yeah, and hopefully very soon. I've been in contact with some people at Xilinx, and they're very interested in using our TFA recipe in their layer.
So from YouTube, Charlie asked what percentage of the target system resource is used needed for the Xen framework infrastructure. That's not something I cannot answer to that because it's a lot more complex than just giving a number. Depending on what you do, it can be down to 0% if your guest does not require any communication with the DOM0, then there will be almost no overhead, apart from the overhead introduced by hardware virtualization, like second level of page tables is introducing an overhead. But there is no definitive answer to that. It's not possible to give a percentage of overhead. Sorry. Any other question?
I think we're there. Thank you, Bertrand and John, for your session.
Thank you, everyone.
So up next, in about 5 minutes' time, status of SoC support in the kernel.
Check this. I found a new microphone. I hope this works better than the one I was normally using.
Hi, and I can hear you clearly.
Very good. Mute again.
Yes.
Can you see? I started sharing the screen as a full screen.
Yeah, I can see that fine. Thank you.
Very good.
Whenever you're ready.
Okay, welcome to my talk on the SoC support in the kernel. My name is Arndt Bergmann. I'm maintainer of the SOC support, specifically the ARM SOC support, and also I'm responsible for bringing in new architectures into the kernel. So I'm also overall the architecture maintainer. And today talk about SoCs overall. The first thing I want to make clear is what it means for an SoC to be part of the kernel. There's like 5 distinct levels of upstream support that one can have in the kernel. There's ideally a platform would be fully upstream supported, which means everything works out of the box. You can install any distro and you expect all the drivers to work. This is the default on most server platforms and on things like PCs. In embedded systems, usually the best you can hope for is that there's a small number of patches that get shipped by a vendor. And with those patches, you can update them to the latest kernel, something works. And then we get all the way down at the bottom, the red one, that means there's a kernel running on a machine, but there's no way anybody is going to touch it anymore. There are no more updates. So what we're focusing on is the 2 green ones, which means people are using current kernels or they will be upgrading to future kernels once they have become the long-term stable releases. The process of supporting a platform upstream is what is usually called bring up. And I think that matches fine with the picture. The higher you get, the better a platform has been brought up. So bring it up all the way means it can basically run forever on any new kernel because everything is supported. And if you only do bring up half the way, you might get to 1 kernel version that you can support, but then you would never have an update on it. So if this is called bring up, then there's obviously the opposite of that, which I would call the bring down. The breakdown happens over time. At some point, people stop running the latest kernels. There might still be the stable releases that somebody has. And over time, people stop moving to the next stable release. They only get updates from a certain vendor. If they get updates at all, then there might only be bug fixes. And at some point, you might have hardware that still runs, but it's not getting any changes at all because nobody is actively building kernels anymore for this platform because nobody cares. So for the upstreaming, there's a couple of things that make it hard for you to upstream a new platform. For the most time that I've been working on this, the main obstacle was GPU drivers. If a platform doesn't have a GPU driver, you're obviously not at the highest level. You need a driver from the vendor to make it work, and that means you still have to have patches. Now, this has changed very substantially over the years, and now for, I'd say, 5 out of the 6 most popular GPUs, there are drivers in the kernel. Most of them working fine in most cases, some not working as well as the others, and there's still one that doesn't have any drivers. Then there's the Android patches. A lot of platforms ship with an Android kernel, and for a long time, there was a huge set of patches maintained by Google specific to Android, and you couldn't actually run an Android user space without those patches. And that, again, has improved a lot over the years. So now you can actually have a mainline kernel, put it on an Android device, and still run all the Android user space. But there's still patches that need to be upstreamed, and this will also continue improving over time. Then a problem that we won't be able to solve is the very short time to market, especially in high-end devices, which have a very short life. There's just no time to upstream everything before hardware hits the shelves. In some cases, patches are not upstream before the last device is sold, and then you're still upstreaming the patches after the device has been replaced by something else. And this is less of a problem for the low-end devices, which tend to have a much longer life. Then there's the short lifespan is directly related to the short time to market, of course. And then there's unannounced products. So some companies are very good at upstreaming all their platform patches before the hardware is even out or before it has been announced. There are some sneaky ways you can get in patches without saying what this product is. You just say a future product will use this new driver. You don't have to actually announce something. But in other cases, that just doesn't work because somebody, like nobody might know that you're working on a specific product line at all in the new market. And then in some cases, SoCs do something new. So there might be new subsystems that are needed. And if there's no subsystem for it, kind of can hack your way around it, write a new driver, but that won't make it into the kernel if there are lots of other companies that have the same need. And then we have to agree on one subsystem first that completely abstracts the user interface so that every SoC can have a device driver for it. What's even worse is if you have more than one subsystem abstracting the same functionality, because then we have to decide which one to use, and that can take even longer time. Now for a world map of the CPU architectures. This is what I, as a kernel developer, imagined the world to look like in 2010. This includes all the machines that were supported in Linux. It doesn't actually include a lot of other things that did not run Linux. And there you can see what the world used to look like back 10 years ago when Linaro was just being formed. So you had a bunch of equally important architectures in all kinds of different markets, from microcontrollers all the way up to the data center. Two things that you don't see on this map are 64-bit ARM and RISC-V, which were both being worked on by a couple of people, but they hadn't yet talked about it in public. So these were clearly not there yet. And in particular, the middle of this picture shows the SoCs. So the SoCs is what I'm interested in at the moment. On the top, you have the data center chips, which tend to be less interesting because they just work in a lot of cases. There's much less variety in the hardware. And then on the bottom, we have platforms that are for microcontrollers, for FPGAs and DSPs, which are all quite different platforms, but they're all are usually not the ideal place for a Linux system, for a general purpose Linux system, or even for most embedded systems. Inside of the SoC bubble, back 10 years ago, we saw ARM, Super H, PowerPC, and MIPS. And what's interesting is that ARM was basically the low end of this. So ARM were the deeply embedded ones, the 200 megahertz ARM9s. They were single core, single issue. They had very little memory, whereas everybody else was going into out of order 64-bit big SMP systems, much larger memory. And also the other thing you see is that all the really nice ones back then were big endian. Then let's look at the generations. I've tried to categorize all the SoCs that we're dealing with into 3 distinct generations. This is a chronological view. So on the left side, you see the things that started appearing in the early 2000s, where you had all those different architectures. You had ARMv5 at some point, you had MIPS, PowerPC, Super H, and lots of other small ones. You had fairly low speed I/O, you had fairly little memory. And then at some point, we started seeing ARMv7, where everything got a little bigger. And then, of course, ARMv8 with 64-bit support. and a lot of high-speed I/O and much larger memory. The low-end parts, however, they tend to stay around for a while because they're still much cheaper. But then again, they're not the same. They sometimes also evolve. So you might have a different kind of low-end platform. But they still fit nicely into these three categories, I think. And the most important distinction that I'm trying to make here is the amount of memory that you have. So in the earlier generation, you had something as little as 2 megabytes of RAM still running Linux. And it didn't really go all that much beyond 128 megabytes. And then the middle generation, you have the larger 32-bit systems for embedded. 256 megabytes was quite a lot a while ago. It's now the absolute minimum. For an ARMv7 system, you have something up to 2 gigabytes typically. And ARMv8 on a 64-bit system, you usually have a lot more memory. So that's 2 gigabytes or more. And then I list all the different interfaces here, but really a lot of the SoCs only have a small subset of those interfaces. But if they have an interface, it's probably in this speed grade. So if you have an ARMv8, you would not see a 2G modem on it. You would see a 4G LTE modem on it, or a high-speed Ethernet. You wouldn't see a 10 megabit or 100 megabit Ethernet. But let's look at the memory usage. So this is a graph that shows all the different kinds of DRAM that I could find just by taking a snapshot of the product listings on Mouser.com. And for every color corresponds to a specific generation of DRAM. And you can see that most of these graphs have something like a V-shaped curve. So on the left, you can see that with every doubling of the memory capacity, the price per gigabyte or per megabyte goes down up to a point, and then it goes up a lot again. And this means, for example, on DDR3, you can spend another 20 cents to double the capacity between 128 megabit and 2 gigabit. But after a point, it gets really expensive. So there's a kind of optimum capacity for each memory device. And you can see how that fits into the generations of SoCs. So as any SoC that might only have DDR1 memory, the optimum point is having 64 megabyte capacity based on the fact that you might only have a single 512 megabit chip. You could have two of them, then you have twice as much. But you can't really have much more than that, or it gets really expensive. And then with DDR2, you get twice as much. With DDR3, you can actually get 2 times or 4 times as much as with DDR2. So the cheapest memory that you can get at the moment is a 4 gigabit chip. In a typical system, you would see 1 or 2 of them on a small embedded system, which means you have either half a gigabyte or 1 gigabyte of RAM total in the system. And this is the ideal operating point, like the ideal marketing point for a 32-bit system at this point. It's also interesting that the 32-bit chips without DDR3, they started disappearing along with most of the other architectures. So if you don't have an ARMv7, you probably don't have DDR3, and then you're already stuck in this lower capacity category, which means it's much less useful because it's always easier to start out with more memory and then just be more wasteful to the memory and have it last longer. And then for 64-bit systems, you are immediately at the LPDDR4 column. So in a 64-bit system, having less than 2 gigabytes of RAM is also not ideal. because then the memory can become quite tight. With 64-bit, you need maybe 30% more RAM capacity for the same workload, just because the pointers are larger and then the code may be a little larger. And that gives a pretty good distinction between the 32-bit systems running DDR3 and the 64-bit systems using LPDDR4. The other thing is on 32-bit, you really don't want LPDDR4 because once you grow beyond 2 gigabytes, it gets really hard. You need high mem, the memory map gets crammed, and it becomes much less, like the advantage of doubling the memory is not really there, but it costs a lot more. So how does this correspond to the memory requirements of distros? So when you look at Debian, which is probably the most commonly used desktop distro on any of these SoCs, the current requirement says 256 megabytes. You can probably do with a little bit less, but if you go below 256 megabytes, it can become painful really quickly. And you have distros like OpenWRT, which now say the absolute minimum is 64 megabytes, but really you should have 128. And this is distro that's highly optimized for memory usage. We can see that this has grown from like 16 megabytes 10 years ago to 128 megabytes right now. Alpine Linux is also a desktop distro that's even more optimized for memory usage than Debian, and they list 100 megabytes as the absolute minimum. An interesting one is the Sonos smart speakers, which were in the news earlier this year because they have deprecated the usage of some of the older machine types. And I had to look it up what they are. So those came out around 2008, 2010, and they were already using old technology back then. And the smallest ones have 8 megabytes of memory installed. And those were still supported up to now with running Linux 2.4, and now they still say they will get bug fixes, but they do not get any new features. So they are in a really tight spot there. And the smallest that I could find is the Microsoft Azure Sphere, which so far is running on one type of SoC that has 4 megabytes of integrated SRAM. So that's the smallest that people are still working on and supporting as of today that I'm aware of. So let's look back at these generations and where these generations are now. The oldest one would be the low-end category. Now these still exist. And when you look at what's out there, these are really the absolute cheapest ones. What's particularly interesting there is that these run all kinds of CPU architectures, whereas the higher end ones, they've all moved to ARM. The low end ones run on all kinds of architectures, including new chips. And these are the ones that I listed, they're all supported by Linux today, or they have patches that have been posted recently. These chips usually cost under $5. You sometimes can get a whole board under $5 running Linux based on any of these chips. But it's really the race to the bottom. You have the absolute minimum that you can use, and every cent counts. So when you get to the point where adding another 20 cents to double the memory capacity breaks your budget, then this is where you're at. And these are usually the same kind of operating point where we used to see ARM9 dominate the world, while the higher end ones were running on other architectures, and it's completely reversed now. And then we have what we currently see as most of the deployments still. The 32-bit ARM v7, we used to have a lot of different systems initially, starting like on the low end, but then starting with the Cortex A8 and then all the other chips up to the A17. What I find most interesting there is that it's consolidating on this one design point where most of the systems that are still being shipped and the new SoCs coming out, they use something like 2 or 4 Cortex A7s. They almost all use 0.5 gigabyte or 1 gigabyte of DDR3 and kind of all end up in the same operating point. There used to be higher speed cores and higher speed interfaces, but those are slowly getting away as people move to 64-bit. And the lower end usually doesn't make sense once you get something for the same amount of money that's significantly better. So if you used to have a Cortex A8 based chip, you can now get a Cortex A7 with 4 cores for the same amount of money. So who's going to buy the Cortex A8 one? And then some of the other exceptions are interesting. So the only chip that is still successful that I could find that's not ARM is the MediaTek MT7621A. That's the MIPS chip that also has DDR3. It's one of the few ones that do. And that's still being put in a lot of Wi-Fi routers. And then the third category, 64-bit, obviously is taking over everything in the long run. But it's not quite there. And it's competing with x86 at the moment. So a lot of the embedded systems have an x86 SoC or regular x86 CPU. Sometimes you get into the same price point with a higher end ARM SoC, but actually most of the market is really x86. So when you're looking at the supported machine types that we see in the kernel, there are on 32-bit ARM, that's really the large majority of all of those. We have way more 32-bit ARM machines than everything else combined. But then again, most of these are also older machines that are probably on their way out in the long run, that have stopped getting updates in field. People might still be using them. They might be running their own code, but the products are on the way of the bring down. When we look at how this changed over time, here we should look at the yellow and green lines. You can see the yellow line is starting to stagnate. So 32-bit ARM, we're still growing, and we're at a much higher level, but the growth is getting smaller. Whereas in 64-bit, there's still the exponential growth that you expect to see from a new platform. And I expect this to go on for another like 5 to 10 years, at which point we'll be removing more 32-bit architectures than adding. So let's look back at the world map and how it's changed. One of the things that happened a few years ago, in 2018, I removed 8 or 9 architectures from the kernel. And these have all been on the bring down path. You can still buy some of these, but none of them have seen kernel updates in a long time. So nobody is working on upstreaming of any new patches because nobody's interested in these. They would run some old 2.6 kernel and not get any updates. And at that point, we just removed them all. Also, a lot of those cores, they still live on in microcontrollers because they are fairly power efficient, and the companies that made them still own them. They might have already had microcontrollers, you just don't run Linux on them anymore. So all of these are consolidating to ARM. Actually, none of those went anywhere else. Then another thing that happened is that a lot of CPU architectures just completely end at some point. These are still all sold. People are still working on them. But after having released new CPUs every 1 or 2 years, all of these stopped getting updates, and these are all the latest generation of a CPU core by one of these companies. And after 2017, they have not released a new one. It may be that I got one or two of these wrong, but most of them I don't expect to see any updated CPU cores. But people are still putting those into products. Then we have seen a lot of migration of users away from the architectures that are kind of obsolete, and also of the architectures that still have a big market share and are not obsolete yet. And these are all moving to either x86 or ARM, so those boxes are getting bigger on our world map. And then we have architectures with new hardware, and that obviously includes x86 and ARM. But there were a few surprising ones. So for RISC-V, I checked, there were actually something like 50 new microarchitectures done in the last year, but not a single product based on that. IBM still has 2 server architectures that are not SoCs, but they still make a lot of money out of those. And then some of the other architectures, people are either shrinking their existing designs or they are making new cores and hope to still have a business beside ARM and RISC-V on the embedded space in the future. One very interesting point that I found is that almost all the big endian ones are getting away. So we have a couple of architectures that have gone away from big endian products, from new big endian products, and just changed the designs to little endian, or changed the software if you can run both of them. We had some companies that used to have big endian MIPS and then moved to little endian ARM. We had those that are just not producing any new chips. And we had those that moved to RISC-V instead of moving to ARM. And the only one that really remains is the IBM Z architecture. So with that move, the world looks like this, and IBM is getting pretty alone in the upper right corner. But we also had new architectures. Most importantly, of course, RISC-V. As I said, there's very little in terms of architectures that we already, like SoC architectures, we already support in the kernel, but everybody thinks they will be big in the future. And Synopsys Arc is similar in a lot of ways, but very different in other ways. So Synopsys Arc, the Arc has been around for 25 years, almost as long as ARM, maybe even, I don't know. It's been around for a long time. They have a fairly active ecosystem. They have had a number of SoCs running Linux, but my impression is they also get more into the space that doesn't run Linux. But it's very hard to know because they don't seem to be as aggressive about upstreaming the platform support. So either there are no platforms, or there are a lot of platforms that they don't actually upstream. And then there's a couple more architectures. Basically, most of these have already been obsoleted by RISC-V. So some companies apparently decided on the move to RISC-V and then decided to upstream their existing platforms because they recognize that having open source support is nice. And then you have some DSPs that we merged a couple of years ago, but these seem to never have caught on a big market running Linux. So they're also running other things, but these are still around. So the new architectures, I put them there. As I said, Arc is huge. They are probably the second most shipped architecture after ARM, but they're not very visible in Linux. And RISC-V I put there because there's a lot of work going on, even if you can't really buy much hardware. Just to prove my point here, I made a list of all the architectures and how the number of change sets in the kernel changes over time, and you can see that 32-bit ARM is already shrinking to half of what it used to be. 64-bit ARM keeps growing, and currently they are roughly the same. So 32-bit ARM, 64-bit ARM, and 64-bit x86, they're about the same, and they make up most of the changes overall. PowerPC had a pretty good run, but they also seem to be declining. And then you have MIPS and S390 as something that you can still see, but they're way at the bottom, and everything else is really in the noise. This is the noise, as you can see. RISC-V now sticks out a little bit at the end, and then you had others like Spark and Arc that had times of activity, but are not really there anymore. So this is where we're at the moment. I get to my predictions for where we will be in the next 10 years. I think that the three architectures, x86, ARM64, and RISC-V, will basically be splitting the SoC market 3 ways. Very hard to tell which one will be bigger, because we hope that it's ARM. Upstreaming will get better. We will still see 32-bit chips get released for a long time, but I think that in 2030, we will have seen the last one getting released. And then probably another 10 years after the last release, while people put that chip into new products, and another 10 years of continued usage of these products. So there's probably another 25 years maybe that people will use 32-bit chips, which is very important to me because I just spent a long time on the 2038 problem. And I don't think there will be any new ISAs. I think that time has gone, but 128-bit computing, either making pointers longer, making physical address space longer, or we got the talk on Morello, and with the Cherry architecture, there was a talk last week that also has a pretty good chance of at least starting to become visible over the next 10 years in products. And I don't think that any of the other ones will still make it. Okay, that's it for my talk. And now I shall have a look at some of the questions. I saw you guys typing away there. So Drew is asking, did you discover ARMv7 systems using more than 2 GB in your research? Yes, I did. There are, most importantly, the TI Keystone 2 systems. There are some that use up to 8 GB, and they will still be around for a couple of years. There's an interesting discussion going on about removing HIMEM support, which would limit the maximum usable size to something like 2 GB for any 32-bit architecture. And if we do some tricks in the kernel, we may extend that to 4 GB. But 8 GB systems, we basically have to wait until they are all in the bring down phase and don't get updates to later kernels anymore before we can actually remove the HIMEM support. And then John asks, are people migrating to ARM and running Big Endian, or actually switching to ARM and Little Endian at the same time? I'd say both happens, but the latter is more common. There are some large code bases where people rely on old code that is not Little Endian safe, and some of those run it on ARM using Big Endian kernels, but it is getting less and less common. And then there's a question in regards to smaller embedded systems. What are the minimum requirements for running Linux besides size of memory? On the philosophical side, could there be Linux without support for MMU? Yes, there's actually a lot of that. I had on one of my earlier slides, I showed there's actually ARMv7M would be an example without an MMU. And we have lots of other systems without MMU, and those tend to be the smallest ones in particular, because there is still a demand for very cheap systems with not a lot of CPU performance, not a lot of memory. And if you have an ARM CPU, that means you probably have a Cortex-M, and they don't have an MMU, but they do run Linux. And that's it from me. Any other questions? Yes, question from Ralph. Can you provide some general info about the SOC tree? What are the criterion for getting code included? Is there a website mailing list? Yes. So this is a topic for a whole new talk, of course. We have the soc@kernel.org address where we take patches that are SOC specific. Usually we take patches from maintainers that are already maintaining an SOC family. But if you have a new SOC and you want to maintain it, or there's already support and in the kernel, but no maintainer left, then soc@kernel.org would be the point of contact. You just write to us if you have something about upstreaming. Generally, we tend to be fairly liberal about adding new SOC support, even if it's very rudimentary. But then if a very rudimentary port stays around for a couple of years, we'd also throw it out very quickly, because it's clear that once the bring up has stopped, it can only go down from there. And if it's not functional, then we can throw it out. Robin asks, in your role as SOC sub-maintainer, are there any specific safety, security, hygiene aspects you care about? I don't think anything specific. We tend to work the same as all the other maintainers. I want to know who I get the patches from. I want signed Git tags when I get patches. Most of the work we fan out to the next level down. So we basically only take patches from the platform maintainers, and we have to trust them to do the right thing. So the main thing we do is we limit the number of people we pull from regularly. And there's a question, is there a specific ARMv7M SOC board that you can recommend for particular ease of getting started? ARMv7M, I generally do not recommend doing any of it. The best supported probably is still the STM32F7. That is the one that I remember last seeing patches for. If you're interested more in NoMMU than ARMv7M, there's the latest one that was added is the 64-bit RISC-V board. That's actually the only RISC-V board that's supported in the kernel. That might be interesting just for fun reasons. I would not recommend any of that for a product. But generally, having like there's the Atmel SAM9X60, which does have an MMU, but is in the same space. So that's the ARM9 CPU that was recently added to the kernel, and that is very well supported and would be in the similar price range as any of the Cortex-M systems. Right. And I think that's it from me. And it sounds like I misread the time there, because it says here it's been 56 minutes.
That's okay, Arndt. That's fine. Thank you very much for your session. Some good questions there. Thank you. So the next session will be at 12:30, and it is Yocto tricks and hacks. So you've got 20 minutes if you want to take a break.
Thank you.
Do you able to see my screen?
Yeah. I just need you
Is
to
the audio clear?
just make it full screen. Click on present.
Yeah. So is the audio clear?
That's fine. Thank you. I'm just going to mute you for a couple of minutes. I'd like to introduce Morthy and the next session, Yocto project tricks and hacks. Thanks, Morthy.
Okay, thanks, Philip. Hello, everyone. This is Murthy, a senior engineer from L&T Technology Services. I'm a Comcast assigned in Linaro. Yeah, we're going to see the tricks and hacks, what we can use in Yocto project for faster development and build. So, yeah. So here we are going to see uh, the usage of Bitbake and Open Embedded Core steps, that how we can make the faster development, how we can hack, and what are the tricks available. And later that, uh, uh, so there will be extensible SDK installer. So that is provided by Open Embedded Core. Few things we will see that, and the things what are all to be handled for Yocto version migration. So migrating your metadata from one Yocto version to another. So these things we will see in this session. So before getting into that, so the options and the hacks, what are all mentioned in the slides, so which are I used in the daily basis, and and if any other things we can, if it is available, so people can share between the audience. Yeah. And I'm having only one screen, so probably at the end of the session, I'll be addressing your queries. So let's start the session. So I'll give a quick introduction. So Yocto project is a Python-based build framework. So this is from open source collaboration. So this build system will allow the developers to create and customize Linux-based systems. So as it is a Python-based tool, it's a powerful tool, and this will be based on cross-compilation, cross-platform builds. So this allow cross-platform builds for a desired target, and this follows some task like a generic task or the common task like source fetching, patching on the application, and configure, compile, and packaging the artifacts which are generated for output analysis, and goes for package generation like IPK or RPM or DEB packages. So also it involves a quality analysis test and generates image as well as the SDK installer. So this Open Embedded Core is a collaborative effort of Yocto project and recognized based on the Open Embedded Core model. The advantages here is it supports most of the major hardware architectures, and it also allow distro-less builds. So without any distro, I mean, you can set distro equal to no distro, and you can proceed a build. So without a distro, you can proceed a build, and it allows to pick only one version for a recipe. So you guys know recipe is nothing but the metadata for a particular component. So if meta layer contains more than one version, it picks the higher version, and if it split up between the two different versions are split up between the meta layers based on the priority or the preferred version it picks. So only one version it will pick from the recipe. So these are all some advantages. So Bitbake is a powerful engine that executes Shell and Python-based tasks from the recipes. So yeah, we'll finish this in soon. Yeah, we'll get into. So also, Meta Open Embedded is a collection of multiple layers. So it contains a supplementary for OE code. So additional packages other than Open Embedded Core you can find in Meta Open Embedded. So collectively, all three these are the basic things for having a Yocto build workspace. So yeah, Bitbake option we'll see. So as you know, guys, these are all the common Bitbake options, and how we can use for the faster development is Bitbake provides option to build to a particular task for a recipe. So -C option provides the to build a particular task. So internally it goes with so Bitbake initially parses the recipe, all the recipes in the meta layers. And once the task is completed, it stores the cache information in the shared state cache. So so once a task is completed, when you try with the -C option, it won't allow to do because already it will be in the cache. So to forcefully do the particular task, -F will be available. So so in this case, if -F is provided for the particular task, the succeeding task will be also scheduled for the next run. Yeah. So another option is -K here. -K will continue even on error. So Bitbake will stop when error throws from the recipe. But to continue with that, -K will provide that. But it stops when all the possible dependencies tasks were completed. At that time, it stops. So this will be useful for whenever you go for a migrating from one Yocto version to another, or if you are reproducing a working build. So at that time, it will list out all your possible errors so that collectively we can fix that. So dependency tree file in dot format. So Bitbake allow you to create that dot file, and also Open Embedded Core provide one tool called OE-depends-dot. It's a tool to read the dot file, and it will be given in a readable format so that you can uh, trace out what are all the dependencies for a particular task. So this -G option will be useful when if any circular dependency errors were observed in while building. So at that time it will be useful. So another option is -B, which is to build the task without any dependency. So on this case, you should give the absolute or the reference path of the recipe. So this will be useful only when the dependency are already built. So only after that, to avoid going through the parsing or all the recipes all over the parsing, to avoid that, -B can be directly given. So without any dependency, that recipe task will be built. So yeah, also Two more options for enabling the debug prints and verbose log. So the debug prints is based on the Open Embedded Core debug levels, and -v verbose log enables the commands which are involved while executing a task. So these are all the big common options that we can utilize for faster execution. So next one is we are seeing how we can override the source revision of a recipe. So before going that, why to override a source revision of a particular recipe is so in general, meta layers provide recipes either by point to a pin revision, or it points to the head of the source tree through auto rev command. So such case, if you want to do vice versa, so if it is auto revision, if the recipe is in auto revision, so without disturbing the recipe, if we want to pin that recipe to a particular revision, so such case we will go for this source rev, overriding the source rev. So this is how we can override a package of a source revision of a package. So this usually we mentioned in the local configuration or the auto configuration. So if you have a working build workspace, so there is a tool available called build history -collect source res. So this is a utility that will list out all the build recipes revisions in this particular format. So after a successful build, if you want to pin all the recipes to a particular revision, so you can collectively take this source revision from this tool, and you can have in auto configuration or in a local configuration, and you can go for a working or a reproducible working build. So this tool will help you that. So the next one is BB source revision policy. So this is a variable provided by Open Embedded Core, which has two options. By default, it comes with cache. So if BB source revision policy is set with cache, uh, uh, all the pin revision or the auto rev will be stored in the cache, and it will retime for the next build also. So once it is set to clear on the next build, if any, it fetches the source tree and finds if any difference between the head. So if it any new revisions find on over the head, so it replaces and build again for that recipe. So it will be applied all over the recipes. So based on your usage, you can switch between the cache or the clear. So in case if you want to build all your components from the head revision, so you can go for clear option. So this is how these are all the variety of options available from Open Embedded Core to override source revision of the recipes. Yeah. So next we see on the how we can conserve the disk space. So usually Yocto takes the data for a one workspace in GB in terms of GB. So in order to reduce that, Open Embedded Core provides one class called RM work. So that will lowers the usage of cache data in the workspace. Also, that will remove your work directory once all the tasks completed for a recipe. So once it got configured, compiled, and packaged everything after the quality check everything, so it removes the work directory, and it maintains all the artifacts, the generated package contents from the cache side. So in general, to utilize this, you have to inherit this package as shown here on your local configuration, or you can, if require, if it is a if it is not a development based build, so you can directly have in your machine configuration or your distro configuration also. So in case if you are in a development to stop removing the work directory for your particular recipe, this rm work exclude variable will be useful. So you can list out your recipes which are not to remove the work directory, that you can assign here. Again, you can use this in your local configuration and list out your recipes. So on using this RM work class, probably around 15 to 20 GB of data you can save in your disk space. Along with that, another option is inhibit package debug split. So this will inhibit the debugging split while packaging. So if you set it to 1, this will prevent the package splitting from the debug info. So by default it will not be set in case if you need that, if you don't want splitting the debug info during packaging, so you can set it to 1. Yeah, another option is DL directory. It's a download directory path for letting the Yocto project, Yocto build framework to download all your source to a particular directory. So this will be how this will be useful on conserving space and for faster builder. In case if you have a sources already downloaded in a particular directory, that directory you can point before starting your build. Or if you are reproducing a new workspace, I mean if you are replicating your workspace again, you can point the download directory which is existing available on your previous workspace. So by pointing for all your build to a common download directory, so your do fetch task for each recipe will be it will be skipped as already the sources were downloaded on your directory. So that is how you can fasten your build and you can conserve your disk space. The next one is the script files for each task of the recipes. So Yocto will generate as I already told, it generates shell or Python based scripts for each task. So the script will be generated and it will be available under the temp subdirectory of the work directory. So so the script will be named as run.do underscore compile or do underscore configure package, like that, with your process ID. Along with that, it has a soft link to point to the current task. For example, run.do compile will be your soft link that points to the current task script. So how we can utilize this is for faster development. So in case if you want to if you are working for a particular task, let's say you are configuring something, you are additionally configuring something for your source. So in general, Yocto recipes will allow you to prepend or append your customized commands for a particular task. Let's say if you have to compile prepend, that will come before this before this auto to I mean the do compile task will be prepended with your customized commands, and exact do compile activity will be later will be called. So this is how a typical task will be generated on this on this way. So the your append also will followed by after your basic task. So directly you can run this script as it changes the directory to your build directory or your source directory. After that, this will call your particular task activity. So you can directly run the script. So if you run this script directly, you can avoid running from BigBake because BigBake will pass all your recipes. So it takes some time. So to make the task very faster execution, so you can directly run the script, or you can add your customized on the same script level. But the disadvantage here is that the changes what you made on the script will not reflect on your recipe, as well as when you run the same task from BigBake, your changes on the script will be go off. because every time the bitbake generates a new script for particular task. So this is how you can, by running this script directly, you can save some time for faster build. So the next one is to have a parallel build. So Open Embedded Core provides some variables to have to take the to take the bitbake to share between your cores. So the BB number threads is the variable that you can tell how many cores you have the bitbake can utilize from your build system. So that this can be either you can uh, hard code or OE already provides some utility for to get the CPU count. That also you can give to utilize the all your cores for the builds. So this can be either it can be hard coded. If suppose if it hard coded more than your CPU cores, it utilizes the available one. Available numbers only it will take. The maximum it supports is 120. Most probably we can use this OE utility CPU count, so directly to utilize all your CPU for your bitbake task execution, or in case if also to make on using make command for your configuration or compilation. Also it supports parallel make to mention the same number of CPU counts to use make and make configure or make compile for the make command. Instead of using -j option, you have to allow using parallel make command variable. Also for installation, parallel make install will be used. This will having your letting you all your cores to be used in parallel, so the build will be faster. So next one is the before seeing this slide, the options what we seen till now uh, is uh, is the Open Embedded Core of variables and the bitbake variables and options available to have the faster builds. The another major feature which is provided by Open Embedded Core is extensible SDK. So Yocto provides generating provides along with generating image. It also allowed to generate your SDK installer. So this is to have your SDK to start developing your application directly on your platform. So this extensible SDK will provide you additional to the normal SDK, the standard SDK. On comparing, it will give you another Yocto environment on your toolchain installer. Along with that, it comes up with dev tool support. It's a dev tool is a powerful package that you can add your recipe or build and package your recipe once the SDK installer is installed on your host machine. So previously, the standard SDK provide let the source to you have to download the source and do make install the same way. To avoid that, this dev tool will fasten your work to just to add your recipe, and you can build directly from this dev tool. So that we will see what are all the commands available in the dev tools that we'll see in the next slide. So the SDK, extensible SDK will come up with two different types. One is full and the minimal. Full will generates SDK installer with the complete bundle which contains the shared state artifacts also. Uh, in general, the generated installer will be in a bigger size, even in GBs also. So commonly we use minimal type, so that will generate only the SDK libraries, so it avoids the libraries and tools other than the SDK. So it generates in single size and it comes with around 500 to 300 to 500 MBs The installer file will be around 500 MB. Also, OE Open Embedded Core provides one tool to publish your SDK to your specific URL. So through this tool, you can mention your URL, so that will publish the SDK for release purposes. So on every installer generation, we need to specifically run this command to publish every time to maintain like versions. Yeah, so this OE provides some tool to publish your SDK. Yeah, let's see what are all the dev tool commands, how we can configure and compile your applications on your installed SDK. So dev tool provides some options to add your recipe. So you need to mention dev tool space add space your recipe name and the source URI, the source tree URL for that source. So through this, it will add the recipe into your SDK installer, and it provides option to upgrade your current version. It can modify your source, and it also allow a editor to open your recipe file in an editor. And through build command, you can configure and compile the source. And directly, even you instead of going for a recipe, you can build the whole image as well. And it can be also allowed to deploy the specific recipe to the target. So these many options will be available from the dev tools, and the slides showing the common things. So this SDK, extensible SDK, will allow you a faster development instead of going for a complete Yocto build. So the thing is, the very beginning you have to go for a Yocto build, then only this extensible SDK installer can be generated. So after that, the one shot you go for a Yocto build, later the extensible SDK that you can generate and go for your application development. Yeah. So
Morthy, sorry to interrupt.
Handle for version
Sorry to interrupt you, Morthy. Can you wrap up soon, please? We've got the next session coming up.
Yeah, okay. Yeah, so this version migration, so the things you need to taken care how the layer is on layer configuration. You need to add the compatibility, and it involves replacing the deprecated functions all over your metadata, and rebasing the patches which are all maintained for the open embedded component versions. And you need to maintain specific VB appends for each version of the open embedded components. So along with that, based on the version migration, the toolchain version will differ. Open Embedded Core provides GCC toolchain, so that based on the higher version, you may face some build errors, so that you need to resolve. So these are the common things on migrating your Yocto version, Yocto to higher version. So these are all the things we covered here. Yeah. So if any queries we can see, or if I miss to address your queries, you guys can post your questions to my email ID, so that yeah, we can I'll address them. Thanks, guys.
Thanks, Morthy. So we've got the next session coming up in a couple of minutes, which is another Yocto session. Nico is going to talk about the Yocto project long-term support in a couple of minutes. So we're just setting up for the next session, which is Yocto project long-term support. Okay, Nico, thank you. You'll need to hide, that's it. Can't hear you if you're talking.
No, I'm not talking, so maybe that's why. I didn't know if I was allowed to talk.
Yeah, you can start your presentation, thank you.
So everything is working fine now, it's full screen and
Yes,
starting?
you can see it clearly and hear you clearly.
Okay, perfect.
Okay.
So, hey everyone, thanks for joining us today in this. This is my first virtual event, so let's see how things are going to go. So I'm here today to talk about something which is happening for the Yocto project, which is a very important event for the project, which is about the announcement we've made recently about the long-term support. So I'm working for Linaro, and I'm also the community manager for the Yocto project. So that's one of the reasons why I'm doing this talk today. So what we are going to discuss, so it's a fairly short amount of time. So I mean, we had to reduce and just go straight to the point. This is what we are going to discuss today. So I want to give a very, very quick explanation about how the Yocto project is organized and the membership. We won't go into any technical details or into too many details about the Yocto project itself, but it's just like a quick introduction and quick overview. Then we'll talk about the current release process that we've been following for, I mean, many years now, which pretty much hasn't changed since the beginning. We talked about some recent improvement that the project has done in terms of automated testing, which is actually one of the reasons why we could discuss about LTS. And then finally, we'll talk about the LTS, how it happened. We'll share some details about that, what it's going to be, and what's going to happen in the next, I mean, very shortly. And finally, I mean, I'm sure you want to help, so how he will be able to help us with this very important change for the project. So let's start. Every Yocto presentation starts with this slide, I think. So basically, what is the Yocto project? So it's not. We have a lot of issues with the terminology. Most people are very confused by, I mean, what the Yocto project is about. So we try to explain that as much as we can. The Yocto project, it's not a Linux distribution. It's not. It's basically a set of templates, all the tools and all the methods that you need so that you can actually build your own Linux system. So it came from the embedded space, and nowadays we see it's used more and more elsewhere as well. But basically, if you have to remember something, it's basically everything, all the tools you need, all the scripts that you need to make your own Linux system. So it's not one specific distro. It can make as many distros as you want or as many Linux systems as you want. The organization itself, so there is a whole organization behind the Yocto project. So it's a project which is hosted by the Linux Foundation, which started in 2010. It was the first collaborative project started by the Linux Foundation back then. The project architect was and still is today Richard Purdy, who most people involved with the project should know by now. The project uses Open Embedded, which is another open source project that was specialized in building a Linux distribution, which started way before that. But there is definitely a very close relationship between the Open Embedded project and the Yocto project. The governing board, so basically the organization is made of members. The members are companies. They are typically Linux Foundation corporate members, and we have different levels of membership based on, I mean, how much the company wants to be involved with the project and how much they can. But basically, we have silver, gold, and platinum level of memberships. membership. And yeah, the company that join the project are the company that want to influence the project direction. Every major decision in the project or change that we make to the project organization or is actually voted by the governing members. But this company also contribute, financially. There is a certain amount of money that we need to actually run the project. Everybody must know by now, but we run many services, build servers, and we also have some websites, and we have many. We have some costs associated with running the project. So that's basically all the member organization that actually, thanks to this company, that we can do that today. The governing board also is nominating and voting for the Yocto project technical steering committee, which is something fairly new in the life of the project, started last year, but that's been established last year, but that's also a big, an important step for the governing member. You have a couple of links here that if you are interested in learning more about the membership structure and how to join the project. And of course, we can always come back to me later if you have any specific questions. The way the day-to-day project is organized is around the governing board, also called the advisory board. And we have different teams, and they are like individuals running. Each of these teams, we have on one side the technical side, the TSC, and which is in charge of all the technical decisions for the project. The governing board is in charge of basically all the business decisions, the budgets, and the general administration for the project. So we meet as much as needed from time to time. And that's how the project evolves and is making decisions. And then on top of that, we have the advocacy team and the community team, where we actually look at things like marketing or organizing events. If you know about the project, you probably have heard or have even attended one of the Dev Day, for example, or the Yocto Project Summit. So that's the kind of things that we organize. So it's people that are involved and closely involved with the project, and discussing these things and making decisions in that regards. So again, that was a very quick intro. I didn't want to have this talk without giving some background about how the project is organized, because that also explains how we ended up with making the decision about the LTS, for example. The current release process. So it's a non-fact, but we basically have been doing two releases a year since the very first 1.0 release. It has never failed. We have sometimes slightly postponed by a month the release, but that's as much as we've done. There is a release in spring, in April, and in October, the fall release. And it's been like that since the beginning. So all the project has a very predictable release cadence. We have this 6-month cadence where we do a bunch of the changes and most of the drastic changes as early as possible in the release cycle. And then we tend to have milestones where we actually have feature complete, and then we start heavy testing of the project. So that's what we are doing. Also, just to avoid some misunderstanding, so what we call a release of the Yocto project is basically what some people would call the pocket tree. That's basically the aggregation of OE core, Open Embedded Core, BitBake, Meta Yocto, and the whole set of documentation as well. So that's basically what we end up releasing every 6 months. What our release usually include, and again, that's usually, it can change, but in the major release, so every 6 months, we can make any change. We can include API changes in all the components. So the project is about the maintenance of all the metadata for the open source project. So we include all the latest version of every project that we support and maintain. We include new features, so we can even break things like in BitBake. We can actually make drastic changes everywhere. We tend to use the LTS kernel version as much as we can, because that's something which is much easier to support for us. We of course fix issues that are reported to the project. There are various ways people tend to report issues to the project, but we try to fix them when we are aware of them. And then, we can make any change on the project. Whether it's infrastructure testing, infrastructure changes, script changes, anything. So basically, every 6 months there are a bunch of changes that we make, and that can one of the consequences of that is that it might be sometimes it might actually be difficult for people to keep up with the amount of changes, and upgrading every 6 months might actually be slightly more difficult than people had wished. So we can add new architecture when that comes, and yeah, any kind of change. One thing which this is actually quite good with this 6-month release cycle is that we have a very tight integration with upstreams. So, I mean, which means that if you use the latest Yocto release, you will be running very likely the most recent software for everything. I mean, all the core components of the Linux OS. We also do stable release. So after we make the fall and April release, we make the dot release, so .1, .2, etc. We have some very strict rules about what we do and how we manage these branches. The first one is it's a very strict backport policy. So your change must be in master first, and then it will be backported. What we accept in the stable branch release is only like bug fixes or security fixes. We don't make changes, upgrade of component. We don't break API. We don't add new features. It's really about stability and fixes. So that's the process we are following with stable release. The testing is very much the same as what we usually do with the regular release. So it all looks good, but there are some challenges along the what we usually do in terms of the maintenance we do for the release is we try to maintain the last 2 previously released and while we work on the next release. So basically that gives like a maintenance window up to 1 year, which is not enough again sometimes for some specific use cases to deal with support. The work is done thanks firstly for people that volunteer their work. It's mostly community time, and it's not something that is funded or financed by the project. It's basically thanks to the community that we're able to do this thing. The testing, which is basically the same, has been the same so far as what the project is doing, is relying on some manual testing, which is done by some of our members. So basically we are doing some overhead on some of the member resources for the manual testing. So that's seen as a challenge, and it's been an issue at times. So we've talked about the project, we've talked about the release, the current release, the stable release process. Over the last 2 years, there's been drastic changes in how we do CI and test automation for the project. We've revisited completely the way we do the CI infrastructure and the CI loop with a new version of the auto builder, and we also bought new hardware to actually run our infrastructure. So we have today, something like 25 recent servers to builders, and we validate more than 12 host distribution. So that's that refresh of the infrastructure was a fairly large expense for the project last year. That was very much needed to actually modernize the builder and actually spend less time waiting for the builds to complete. So that was one part of the change. The other part has been also discussed quite a bit last year in various places and articles, but there has been a lot of work to actually reduce the need for manual testing. So we used to have a huge amount of manual testing everywhere in the system, even like in every piece of the system. And a lot of work has been put together, led by Richard and the rest of the community to actually try to do more and more test automation. Whether it's running more p-tests and adding support for more p-test. P-test is the test automation we use for packages in Open Embedded. We've been extending and running LTP, and we've also done a lot of test automation in terms of test reproducibility. What we end up with basically is when we do like a full automated test for a build, we almost run 2 million tests in 8 hours across all architecture that we are interested. So it's and if you had seen what we were doing in the past, this is like a stunning number that we can do today. So all in all, the limitation and the issues and that we have seen with the stable release and the improvement that we have seen in terms of automated testing have led and opened up the discussion for LTS. So how it happened and why it happened. As we said, I mean, the 6-month release cadence, it aligns very well with the pace of open source. I mean, open source does, I mean, release as often as possible, and that's actually really good. However, when we have some people using the Yocto project and trying to make some product on their own use case and on some specific markets, making a product takes more than 6 months. So basically, by the time you are ready to make your product, ship your product, I mean, you are already using release, which is not the latest one. So what we see is that many companies out there that are using the Yocto project release, they just end up doing their own LTS on their own. So basically what they do is they start their own, they pick a release, and obviously, I mean, every company is going to pick a different release, and everybody is going to try to do, I mean, LTS on their own, trying to backport security fixes, backport bug fixes, and so on. And most of the time, what we see is they do that behind their closed doors. So I mean, we don't even know about what's happening. So over the years, it has become like one of the big main complaint that we hear when we meet, I mean, developers at the events that we organize, the BOF that we do at, I mean, the LF events. That's what we hear. I mean, people would like the project to make a decision and do something about LTS. So what happened is that at the last ELCE, it was in October 2019, the TSC has come up with a proposal to the governing board on how and what we should be doing for LTS. There has been obviously a bunch of discussions within the governing board about, I mean, whether that, I mean, why and the value of doing that, and the pros and cons, etc. And we've been very happy that we were able to announce back in, I mean, in March, like earlier in March, that we would be doing LTS moving forward. So you have the link to the announcement here. So again, I mean, what is important here is the process and how things happen. I mean, so that's all the changes that have happened. So I mean, we were in a position for the TSC to make the proposal. So what the LTS proposal is, I mean, at least from the high level perspective. So we want to have an LTS every 2 years. So we want to have something which is predictable. People know when the next LTS is, and people can rely. So the idea is that we want to, all the companies that use the Yocto project and that need LTS, instead of picking their own version, they will start aligning on one single version. So at least we align all the companies out there on a single version. The project will maintain that LTS for 2 years. It won't be like for 1 year as we do today. It will be, I mean, maintained for 2 years. The maintenance of that branch will actually be funded by the Yocto project membership. It won't be community time. So we have evaluated that, or we have basically approved a budget for someone to work half time basically as maintainer, official maintainers for that branch, and we expect that it will actually be very helpful for the project. We are currently, I mean, in process of hiring and trying to finalize and find someone, and we will be announcing that later in April. The next release in April, or actually very soon now, the 3.1 release will be the first LTS. So everybody is aware that this is going to be the first LTS. And hopefully what we will see is that people will start aligning their use of the release toward this release. One consequence of that, because we have this LTS every 2 years that will be maintained for 2 years, that the intermediate stable release, so the one that will not be LTS, we will reduce their maintenance to 7 months. 7 months, so that it actually is helpful for companies that want to switch from release to release. They have like a window where they are still maintained for the current release until the next release is ready, and so on. So so basically what we think is with this setup, we are going to address the need of people who want to use switch from release to release without to worry about the LTS. We also want to address the need for companies that are very interested into the LTS. And finally, of course, we don't want to discourage anyone to leave on master and just keep using master or keep developing against master branch. Of course, everything remains under the responsibility of the TSC. The LTS release process as the regular process, and the maintainer. So the maintainer will basically report his time and report his work to the Yocto project TSC. A bit more details about what we want to do. The components that we will be covering are the components that are included into the Yocto project release today. So same as in the very first slide, BitBake, OECore, Meta Yocto, the Yocto documentations. Of course, we are not going to cover all the layers that exist, especially, I mean, Meta OE is not included. Every vendors and yes, I mean, different layers are not included. We will probably encourage every owners of these layers and maintainers of these layers to align with our, I mean, the Yocto project LTS process and release as well. And we think it will happen over time. What we will do is we will only support a subset of the native build platform. I'm talking about the host distro, like basically what you use on your host. I mean, as you know, I mean, the Yocto project supports a wide variety of host distro. Over time, it's very complex to actually run like an old version of Yocto on like a very recent version of like one of the Linux distros. So we'll see and we'll announce when we start the LTS for every release which exact distro we support, but you might expect to have like things like Ubuntu, for example, LTS will be supported. So that will be announced when we actually make the release. We have some tools and mechanisms, it's called build tools, where we actually generate some binaries that are useful to run, to build an old version of Yocto with a newer distro, which we hope will be also useful for people. And we'll see, and we'll see, I mean, as time goes. In terms of the testing, we'll also make some change. We will rely on the project auto builders, of course, and we will only run automated testing. So the improvement that I've been mentioning before, and we will only run on virtualized platforms. We will not be running on any actual hardware. So what the project is doing is we will maintain LTS for the project as a whole, but we will not be testing on actual hardware. There are tools like CV checks or CV tools that we will look at using and deploying as well to make sure that we understand what we are doing in terms of the security fixes. So what it is, what is not, we've had some interesting discussions on the mailing list since we've made the announcement. Just to clarify, so what this is a major change for the project. It's a significant expense for the membership. And that's our response to something that we've heard over the many years about something that was needed for the project. It's an initiative where we want to create a place for everybody to collaborate, again, by making sure that every 2 years there is one main release, which will become LTS. We expect that people will start all working against the same branch, at least the companies that are willing to help and willing to use the LTS. And we want to make sure that people will start more collaboration. So we will provide a full-time a maintainer for the branch founded by the project. That engineer won't be enough to actually fix all the bugs and all the security fix, but what we hope is that we will create the opportunity for everybody to collaborate and work with this maintainer and the rest of the community to make sure that our LTS gets better and better. It's something we definitely have a guarantee that we will have all the resources available to do the integration of all the patches that we see that are addressed against the LTS, and we have testing resources as well, so that we can actually make the release and fast release as much as needed. One issue that I've not said, I mean, we didn't have a mechanism to do fast release before, like the stable release. So to date, I mean, require like the full testing cycle, including manual testing and so on. So that was never really like a fast release. So as important as it's also very important to say what it is not, it's definitely not a replacement for anybody out there that actually offers commercial support. I mean, there are many companies that are in the Yocto project ecosystem, OSVs, that actually offer like very long-term support. We are talking 5 years, 10 years, and probably even more, I'm sure. That's not what we want to do. What we want to do is to enable, the community to work together, at least to enable one main LTS every 2 years. We won't be able to guarantee that every single CV fixes will be there and will be integrated. We guarantee that we have somebody that will be there to work with the rest of the community and the rest of the companies, but there is no guarantee that all CV will be fixed. And of course, we won't be checking, custom, every product is going to be using many different layers. So what we will be doing is LTS for the core components, as I mentioned earlier. So with that said, how you can help, or how can you help us? There are definitely many different ways. The first one is what we really hope is that everybody will start contributing and share bug fixes, CV and security patches. I mean, that's the most important thing. I mean, if we all work together, I mean, that will actually make the project a whole lot better for everybody else. So that's what we all want in the end. So we want to everybody to share a little bit of the pain of the maintenance and this and the bug fixes, and then we enable that and make release for everybody else. You can test the LTS. I mean, nobody makes a product with just a Yocto release. Everybody adds their own distro, their own base port, and so on. So test LTS, test with your distro, test with your base port, and report the bugs. And of course, for us, I mean, we started the LTS, but we don't want to stop, I mean, the development of the project. I mean, master branch remains our main development branch. So if you use master branch and you develop against master, continue to do so. We definitely don't want, I mean, only the LTS to be there. We definitely want to see more and more contribution on the master branch as well. And one thing you can do as well, if you can as well, is join the Yocto project and support the Yocto project and become a member. The hope is that this LTS thing will give us more membership eventually, and we can probably extend, I mean, maybe the duration or what we do for the LTS and so on and so on. So I think it's 25 minutes. And on the last slides, I mean, you have various ways you can find us and reach out to us. I think that's the end. So thanks for listening. If you have any specific questions, I mean, you can join one of the mailing lists. I mean, reach out to the mailing list or find us on, I mean, IRC anywhere. You can talk to me directly as well, and I'm sure I can. If I don't have the answer, I can find the answer for you. So thanks for listening today, and hopefully you will all start testing and using the LTS soon.
Thanks very much, Nico. Much appreciated. And that is the end of Linaro Tech Days. Thank you to everyone who's attended. We've got another webinar tomorrow and Thursday, so please take a look at the schedule to see when they are and to see if the topics are of any interest to you. And once again, thanks very much for joining.